Look up at the night sky, and for a moment, forget everything you think you know about the universe. We often picture it as a silent, empty expanse, a dark ocean dotted with islands of light. But what if that isn't the whole story? What if space isn't empty at all, but brimming with memory? Not in the way we remember our childhood or a favorite song, but in a far deeper, more fundamental sense, etched into the very architecture of reality itself. Imagine the cosmos not as a void, but as a grand, living tapestry. Each thread, each connection, each delicate filament in the great cosmic web holds onto echoes of events that unfolded billions of years ago. This isn't just poetry. It's a revolutionary idea emerging at the frontier of cosmology, that the universe remembers. This concept transforms how we see everything. It suggests that the distribution of galaxies, the vast voids between them, and the shimmering networks we call the cosmic web are more than just structure, they are a record. A chronicle of cosmic evolution written in the language of gravity, dark matter, and time. From the faint afterglow of the Big Bang to the formation of the first stars, every event has left a mark on the fabric of space, like fingerprints on glass. And now, for the first time in human history, we're learning how to read those fingerprints. We're beginning to trace the memory of the universe itself, uncovering stories of collapse, creation, and connection that challenge our understanding of existence. In this video, we embark on a journey to explore one of the most profound mysteries of our time. We'll venture through cutting-edge theories of how memory is woven into physics, decode the hidden narratives within the cosmic web, and ask what this means for our own place in this remembering universe. This isn't just about science, it's about reimagining reality. It's about seeing the cosmos not as something separate from us, but as a dynamic, archival presence that has, in some way, been keeping track of it all. So settle in, open your mind, and get ready to see the night sky and everything beyond it in a completely new light. Picture the universe not as a random scattering of stars, but as an impossibly vast, three-dimensional spiderweb stretching across billions of light years. This is the cosmic web, the largest known structure in existence. Its brilliant nodes are massive galaxy clusters, each containing thousands of galaxies. They are connected by long, delicate threads of gas and dark matter, and between them lie immense, empty voids so large they defy human comprehension. For a long time, we saw this structure as a beautiful but static outcome of physics, a simple result of matter clumping together over time. But what if it's so much more than that? What if this web is the universe's own history book, and every single filament, every cluster, is a sentence in a story that began at the dawn of time? This is the revolutionary idea gaining traction in cosmology, the cosmic web as a memory structure. Think of it like the rings of a tree. You can cut into a tree, and by counting and measuring those rings, you can read its history, the years of abundant rain, the seasons of drought, even the scars of forest fires. The cosmic web functions in a strikingly similar way. The specific pattern of its structure, the precise placement of a galaxy cluster here and a vast void there, isn't accidental. It's a direct imprint, a fossilized record of the universe's earliest moments. Those initial, minuscule quantum fluctuations that were born in the first fraction of a second after the Big Bang were stretched during a period of rapid expansion called inflation. They became the blueprints, the seeds for everything that would follow. Over the ensuing billions of years, gravity acted as a master sculptor, patiently working from that blueprint. It gently pulled matter, both the dark matter we can't see and the regular matter that makes up stars and planets toward those slightly denser regions. This slow, relentless process amplified those tiny seeds into the magnificent web we observe today. So, when we map the universe with powerful telescopes, we aren't just making a picture of where things are now. We are effectively looking back in time. We are seeing the preserved consequences of those primordial events. The gravitational collapse of an enormous cloud of gas that formed a supercluster, the influence of an unseen dark matter halo guiding the motion of galaxies, the echo of a pressure wave from the infant universe that now appears as a preferred distance between clusters, these are all memories. By meticulously studying the geometry of this web, the thickness of its filaments, the size of its voids, the way galaxies cluster at specific intersections, cosmologists are learning to decode this information. It's a form of cosmic archaeology, where instead of digging through layers of Earth, we peer deeper and deeper into space, which also means further and further back in time. This perspective utterly transforms our view of cosmology. The universe is no longer a collection of objects to be catalogued, but a dynamic, evolving entity that has encoded its own autobiography into its very fabric. We are just now learning how to read it. To truly grasp how the universe remembers, we must journey back to its very first whispers, a fraction of a second after everything began. In that initial, unimaginable fireball of the Big Bang, the cosmos was not smooth and uniform. Instead, it was a seething, turbulent sea of energy, and within it, on the smallest possible scales, reality was fizzing with tiny, spontaneous fluctuations. These quantum ripples, these minute hills and valleys in the fabric of spacetime, are the absolute earliest memories the universe ever formed. Think of them as the very first lines ever written in the cosmic history book, inscribed when the universe was less than a trillionth of a second old. But how could something so infinitesimally small possibly matter? This is where the story gets truly remarkable. Immediately after its birth, the universe is thought to have undergone a period of exponentially rapid expansion known as inflation. This wasn't just fast growth, it was a staggering stretching of spacetime itself, and it took those tiny quantum ripples and blew them up to absolutely enormous sizes. Those microscopic hills and valleys were stretched across the entire cosmos, frozen into the fabric of the universe as subtle differences in density, slightly denser regions where a little more matter existed, and slightly less dense regions with a little less. This process created a specific pattern, a unique fingerprint that was imprinted across the entire sky. This pattern is not random. It carries within it specific information about the physics of that hyper-accelerated expansion, its energy, its duration, and how it ended. It is, in every sense, a direct snapshot of the universe's initial conditions, a baby picture preserved for all time. For billions of years, this pattern simply existed, a silent blueprint waiting for its moment. Then gravity went to work. It is an irresistible force that attracts matter to matter. So, over eons, gravity began to gently pull material toward those slightly denser regions. The blueprint started to become a reality. The denser patches began to grow, attracting more and more gas and dark matter, slowly evolving into the first vast clouds that would eventually collapse to form galaxies and clusters. The less dense regions, conversely, were drained of material, expanding into the immense, empty voids we see today. The entire grand architecture of the cosmic web, the great filaments, the massive clusters, the dark, empty voids, all of it is a direct physical consequence of that initial imprinted pattern. The universe didn't just grow randomly, it grew according to this preserved memory of its own birth. And we can actually see this memory today. The afterglow of the Big Bang, what we call the cosmic microwave background radiation, is our most powerful window into this primordial past. This faint light, which fills every corner of the universe, was released when the universe was only 380,000 years old, long before the first star ever twinkled. When we point our most sensitive telescopes at this microwave sky, like the Planck satellite, we don't see a uniform, featureless glow. We see a mottled map of tiny temperature variations, warmer spots and cooler spots. Those spots are the direct descendants of those original quantum ripples. The warmer regions correspond to those slightly denser areas, the cooler regions to the less dense ones. We are literally looking at a detailed, high-contrast image of the universe's oldest memory. By studying this map with incredible precision, cosmologists can read the story encoded within it. The statistical properties of these hot and cold spots, their size, their distribution, their correlation, tell us a detailed story about the physics of the infant universe. It tells us about the amounts of dark matter and dark energy. It confirms the theory of inflation, and it gives us the parameters that govern the expansion of everything we see. This ancient light is therefore the ultimate historical document. It directly connects the universe we live in today, with its glittering web of galaxies, to its mysterious and violent origins. Every filament, every cluster, every single structure we see around us can trace its lineage back to a specific fluctuation on that microwave map. The memory wasn't just preserved, it was the very instruction manual for building a cosmos. But if the cosmic web is the universe's memory, then dark matter is the paper on which that memory is written. We've talked about the blueprint, the primordial imprints from the Big Bang, but a blueprint is useless without a stable, durable material to build upon. For our universe, that material is dark matter. It is the invisible, ghostly substrate that makes up the vast majority of the universe's mass, and it possesses a unique property that makes it the perfect cosmic archivist. It is incredibly boring, and that's its greatest strength. Unlike the regular matter that makes up you, me, and every star we can see, dark matter doesn't interact with light or electromagnetic forces. It doesn't bump into other particles, it doesn't form atoms, and it doesn't experience the complex pressures and friction that shape the lives of stars and galaxies. Its only language is gravity. This profound simplicity is what makes it the ultimate keeper of cosmic history. After those initial density fluctuations were imprinted, gravity began to pull both dark matter and regular matter toward the denser regions. But their journeys quickly diverged. Regular matter, the baryonic stuff, is messy and complicated. When gas falls into a growing gravitational well, it can heat up, collide with other gas, form stars, and then have those stars explode in supernova. These violent, energetic events blow material back out, stirring things up and erasing some of the finer details of the initial conditions. It's like trying to write a message on the surface of a stormy ocean. The waves constantly wash over it, blurring the words. Dark matter, on the other hand, experiences none of that chaos. It simply responds to gravity's call, flowing smoothly into the potential wells and staying there. It doesn't collide, it doesn't heat up, and it doesn't explode. Once a clump of dark matter forms, it remains, essentially, frozen in place. This means the overall distribution and structure of dark matter across the cosmos has remained remarkably unchanged for billions of years. It holds a pristine, unaltered record of the universe's gravitational history, a fossilized map of where things were and how they were moving when the cosmos was young. The beautiful, intricate cosmic web we see traced by galaxies is in fact just a faint echo, a shadow, of the true dark matter architecture. The galaxies are like glitter sprinkled on the surface of an invisible, deeply sculpted sculpture. They show us the shape, but the dark matter is the shape. We cannot see this dark matter scaffold directly, but we can see its gravitational effects with stunning clarity. This is where sophisticated computer simulations become our most powerful time machine. Cosmologists can create a virtual universe inside a supercomputer, starting with those initial quantum fluctuations and then letting the known laws of physics play out over billions of simulated years. In these simulations, they can track the dark matter separately from the regular matter. What they reveal is breathtaking. The dark matter forms a delicate cosmic spiderweb first, a complex network of filaments and nodes known as the cosmic skeleton. Only later does the regular gas and dust, the baryonic matter, follow the gravitational roadmap laid out by the dark matter, flowing along the filaments and pooling at the intersections to eventually form the galaxies we observe. The simulations show that without this dark matter scaffold, the universe would look utterly different. Galaxies would not have had the time or the structure to form in the way that they have. The memory of the early universe would have been lost to the chaos. Observations powerfully confirm what the simulations predict. We can see the gravitational hand of dark matter at work everywhere. When we observe how galaxies within a cluster move, they are zipping around far too quickly to be held together by the gravity of the visible stars alone. There must be a huge halo of unseen dark matter providing the extra gravitational glue. Even more strikingly, we can use a phenomenon called gravitational lensing to literally map the dark matter. The gravity of a massive object, like a galaxy cluster, warps the fabric of space-time, bending the light from more distant galaxies behind it like a giant lens. By studying this distorted light, astronomers can calculate the mass of the cluster causing the distortion. Time and again, they find that the vast majority of that mass is invisible. It is the dark matter halo. These observations allow us to trace the outline of the hidden scaffold, confirming that it perfectly matches the predicted structure of the cosmic web. Through these incredible tools, we are not just inferring the presence of dark matter, we are actively reading the ancient, undisturbed story it has preserved since the dawn of time. So if dark matter provides the stable, unchanging canvas of cosmic memory, then baryonic matter is the vibrant, dynamic paint that brings the detailed picture to life. This is the ordinary matter we know and love, the protons, neutrons, and electrons that coalesce into everything we can see: stars, planets, nebulae, and ourselves. While dark matter's gravitational pull laid down the fundamental architecture of the cosmic web, it is the complex and often violent life cycle of baryonic matter that etches the finer details into that structure, adding rich, intricate layers to the universe's historical record. This process transforms the cosmic web from a static fossil into a living, breathing chronicle. Think of it like this: dark matter constructed the grand, cathedral-like vaults and arches of the cosmos. But baryonic matter is responsible for the stained glass windows, the intricate carvings, and the fading murals that tell specific, detailed stories about the history of the building itself. These stories are written through immensely powerful events. When a critical mass of gas collapses under its own gravity and ignites fusion, a star is born. But that star doesn't just shine quietly. It eventually dies, and its death is where the real storytelling begins. For most stars, this finale is a supernova, a cataclysmic explosion that blasts newly forged heavy elements like carbon, oxygen, and iron out into the surrounding space at incredible speeds. This ejected material doesn't just vanish. It slams into nearby clouds of gas, compressing them, enriching them with these new complex elements, and potentially triggering the collapse that forms a whole new generation of stars and planets. This is a powerful feedback loop. The death of one star directly influences the birth of others, and that event is physically recorded in the chemical composition of the new stars. By analyzing the light from a star, Astronomers can read its unique elemental signature, its metallicity, and know the story of the generations of stars that lived and died before it to create those very elements. This is a form of chemical memory, a lineage of cosmic recycling written into the very atoms of every galaxy. But the influence of baryonic matter goes far beyond just sprinkling new elements around. These processes actually reshape the cosmic web itself, physically altering the memory structure that dark matter so dutifully preserved. Supernova explosions generate immense shock waves that can heat vast reservoirs of gas, preventing it from cooling down and falling into a galaxy, effectively putting a brake on star formation. Even more dramatically, at the hearts of most large galaxies lurk supermassive black holes. When these monsters actively feed on surrounding matter, they don't do so quietly. They become quasars or active galactic nuclei, launching jets of energy and matter that travel for hundreds of thousands of light years. These jets pour enormous amounts of energy back into the galactic environment, heating the gas to such extreme temperatures that it cannot collapse to form stars. This is another profound feedback mechanism. A black hole's feeding frenzy can effectively sterilize an entire galaxy, shutting down its star-forming factories and leaving a permanent mark on the evolution of that entire region of the cosmic web. The pattern of where galaxies are actively forming stars and where they are quiet and passive is not random. It is a direct map of where these violent baryonic feedback events have occurred over billions of years. Furthermore, baryonic matter weaves another, more subtle thread into the cosmic tapestry: magnetic fields. As ionized gas moves through the universe, it can generate and amplify vast, invisible magnetic fields that stretch along the filaments of the cosmic web. These fields, though weak, can influence how gas flows, how cosmic rays travel, and how matter collapses. They represent another layer of information, a magnetic memory of the dynamic history of the gas itself. All of these processes together, chemical enrichment, energetic feedback, and magnetic field generation, mean that the cosmic web is not a finished, static monument. It is a dynamic, ever-changing record. It is a chronicle that is still being written, with each new supernova and each black hole outburst adding another sentence, another footnote, to the grand story of the universe. The dark matter scaffold gives the story its plot and structure, but the baryonic matter provides the vivid characters, the dramatic twists, and the rich, descriptive language that makes the history truly come alive. Now, let's take a conceptual leap into one of the most mind-bending ideas in modern physics, a principle that suggests the universe might be storing its memories in a way that defies our everyday intuition. We've seen how memories are physically etched into the cosmic web, but what if that entire three-dimensional structure is itself a projection, a kind of cosmic illusion? This is the core of the holographic principle, a theory that emerged from the study of black holes and has since rippled out to transform how we think about information, reality, and memory itself. The story begins with a profound puzzle about black holes. When an object falls into a black hole, it seems to vanish completely, its information lost forever behind the event horizon. This presented a direct conflict with a fundamental law of quantum mechanics. Information cannot be destroyed. The brilliant work of physicist Jacob Bekenstein and later Stephen Hawking showed that a black hole's entropy, which is a measure of its information content, is not proportional to its volume, as you might expect, but to the surface area of its event horizon. This was a revolutionary clue. It suggested that all the information describing everything that had ever fallen into the black hole could be entirely encoded on its two-dimensional boundary, like a movie being stored on the surface of a DVD. The three-dimensional world inside the black hole would then be like the projected image from that DVD, a hologram. The holographic principle boldly proposes that this might not just be a quirky property of black holes, but a fundamental feature of our entire universe. It suggests that all the information contained within any given volume of space, every particle, every force, every event that occurs within it, can be fully described by physics that exist on the boundary enclosing that volume. Our reality, with its rich three-dimensional depth, might be a magnificent projection from a two-dimensional surface at the very edge of the observable universe. If this is true, then the cosmic web, with its vast, complex structure, is not the primary storage device. It is the projected image. The true repository of cosmic memory would be on this distant, fundamental surface. So what does this mean for the idea of cosmic memory? It recontextualizes everything. The filaments and nodes of the web, which we've been discussing as the physical imprints of history, might be better understood as data streams, dynamic pathways along which information is processed and translated from the boundary into our three-dimensional experience. The evolution of the universe from the Big Bang to the present wouldn't just be a story written in the positions of galaxies. It would be a computation unfolding on this cosmic hard drive, with the changing structure of the web reflecting the ongoing processing of information. In this view, memory isn't just stored in the universe's very existence is a form of memory, a persistent pattern of information. This principle finds its most concrete realization in a concept known as the AD/CFT correspondence, a specific mathematical duality proposed by physicist Juan Maldacena. It provides a full dictionary for translating between a gravitational theory in a warped anti-de Sitter space, a volume with a boundary, and a conformal field theory, a quantum theory without gravity living on its boundary. While our universe isn't exactly an anti-de Sitter space, the correspondence is a powerful proof of principle that a holographic description of reality is not only possible but mathematically robust. It hints at a universe where the laws of gravity that sculpted the cosmic web emerge from a deeper, more fundamental layer of quantum information theory. The implications for cosmology are staggering. It suggests that the search for the theory of quantum gravity, the holy grail of physics, might be a search for the rules that govern this cosmic information processing. The primordial fluctuations that seeded the cosmic web might be understood as fluctuations in this underlying information field. The holographic principle doesn't invalidate our earlier discussions about dark matter and baryonic feedback. Instead, it offers a potential deeper explanation for why those physical laws exist and how they conspire to preserve information so effectively. It proposes that at its heart, the universe is not made of stuff but of bits. And if that is true, then the cosmic web is the most magnificent read out of that data we could ever hope to see, a constantly updating display of the universe remembering itself into existence. Yet for all this talk of cosmic memory and intricate structure, we must confront a powerful, universal force that seems to oppose it all: entropy. The second law of thermodynamics tells us that the universe, left to its own devices, inevitably slides toward a state of maximum disorder, a featureless, lukewarm soup where all gradients have evened out and nothing interesting can ever happen again. It is the ultimate eraser, the great cosmic forgetter. So how can the universe possibly preserve a detailed, multi-billion-year history if its fundamental tendency is to dissolve all information into noise? This paradox leads us to one of the most fascinating intersections of physics, where the concept of memory directly battles the relentless march of disorder. To understand this, we first need to reframe what we mean by information. In physics, information isn't just abstract data, it is deeply physical. It is the specific arrangement of particles, the distinct state of a system. A broken cup and an intact cup contain the same number of molecules, but their information content is vastly different because of how those molecules are arranged. Entropy is essentially a measure of the number of ways you can rearrange a system without changing its overall energy. A high entropy state is one with many possible, indistinguishable configurations like the scattered pieces of that broken cup. A low entropy state has very few configurations like the carefully arranged intact cup. So when we say entropy increases, we are saying the universe is moving from unique, specific states toward generic, common ones. It is forgetting its initial conditions. This is where the cosmic web presents a stunning defiance. Its complex, specific structure is the antithesis of a high entropy, forgetful state. It represents an enormous amount of information preserved against the tide. How is this possible? The answer lies in gravity. While most everyday processes increase entropy, gravity operates differently. In the beginning, the universe was remarkably smooth and uniform, a very high entropy state for a gravitational system. As gravity acted over time, it took that smooth distribution and crafted it into the intricate, structured cosmic web of clusters, filaments, and voids. This might seem like it decreases entropy, creating order from chaos, but that's only from our limited perspective. For a self-gravitating system like the universe, this clumping is actually the path to maximum entropy. A black hole, the ultimate gravitational clump, is also the object with the highest possible entropy within its volume. The cosmic web, therefore, is not an anomaly in the fight against entropy. It is the universe's preferred, highest entropy way of remembering. It is the most efficient and stable filing system for all the information generated since the Big Bang. This idea connects to a profound principle in information theory, Landauer's principle. It states that for information to be erased, for a memory to be forgotten, it must release a tiny, minimum amount of heat into its environment, thereby increasing entropy. Conversely, to preserve information, you must prevent this erasure. The universe, informing the cosmic web, has effectively built a system that makes erasing information incredibly difficult. The gravitational bonds that hold galaxies in their clusters and the vast, stable structures of the cosmic web represent immense wells of potential energy. To truly erase the information stored in the position of a single galaxy, you would have to somehow smooth out the entire cosmic web, which would require an impossible amount of work and would, in the process, create a catastrophic amount of entropy. The very gravitationally bound structure of the universe acts as a fortress, protecting its historical data from being overwritten by the constant background noise of the cosmos. This cosmic safeguarding of information has a direct and profound connection to the arrow of time itself. Why does time only move forward? The prevailing theory is that the forward direction of time is defined by the increase of entropy. We remember the past and not the future because the past is a state of lower entropy. The cosmic web, as a massive, low-entropy structure from the early universe, is the physical anchor for our arrow of time. Its preserved information gives time its directionality. Without this preserved structure, if the universe had remained a smooth, high-entropy gas, the concepts of past and future would be meaningless. There would be no history to trace, no story to tell. The universe's resistance to cosmic forgetfulness is therefore not just a neat feature. It is the very reason we can experience a flow of time and engage in cosmology at all. The memory held in the shape of the cosmic web is the clock by which the universe ticks, a permanent record ensuring that what happened then is fundamentally different from what happens now. This remarkable process of cosmic archaeology relies on a few key technological marvels that allow us to peel back the layers of time. The most fundamental tool in this endeavor is the measurement of redshift. As the universe expands, it stretches the very fabric of space, and in doing so, It stretches the wavelength of light traveling through it. The farther a galaxy is from us, the faster it appears to be receding due to this expansion, and the more its light is shifted toward the red end of the spectrum. This redshift, denoted by the letter Z, acts as a direct proxy for both distance and look-back time. A galaxy with a high redshift is not only very far away, but we are seeing it as it was in the very distant past. By meticulously cataloging the positions and redshifts of millions of galaxies, we can create three-dimensional maps of the universe's large-scale structure, effectively stacking slices of cosmic time on top of one another. The most ambitious of these projects, like the Sloan Digital Sky Survey, have painstakingly mapped the locations of over 1 million galaxies, revealing the cosmic web in stunning detail and allowing us to watch its evolution unfold across billions of years. These vast maps are just the raw data. The real detective work begins when we start to interpret the stories they tell. The distribution of galaxies isn't random. They cluster along the filaments and nodes of the web in very specific ways, and by analyzing the statistical patterns in their clustering, cosmologists can infer the underlying physical processes that shaped them. For instance, the phenomenon known as Baryonic acoustic oscillations provides a cosmic ruler etched into the very fabric of space. In the early universe, pressure waves traveled through the hot, dense plasma, creating ripples. These ripples froze in place when the universe cooled enough for atoms to form, leaving a characteristic preferred scale, a standard length of about 500 million light-years, imprinted on the distribution of matter. By measuring this same scale in the clustering of galaxies at different epochs, we can precisely track how the expansion rate of the universe has changed over time, reading the history of dark energy's influence directly from the architecture of the web. Furthermore, by comparing the cosmic web we see at different redshifts, we can witness its dynamic evolution in action. In the early universe, the web was more delicate, a faint network of nascent filaments. Over time, gravity amplified these structures. We can observe how small galaxies, drawn together by their mutual gravitational attraction, merge to form larger ones. We can see how gas funnels along the dark matter filaments, feeding the growing giants at the intersections. The scars of past collisions are often still visible tidal tails of stars stretched out between interacting galaxies, or the disturbed, chaotic shapes of recent mergers. Each of these features is a chapter in a galactic biography, a memory of a dramatic event that shaped its current form. By simulating these processes with immense supercomputers, we can test our theories of physics against these observed histories, checking if the virtual universes we create develop memories that match the real one we inhabit. This constant dialogue between observation and simulation is the engine of discovery in cosmic archaeology, allowing us to not just see the fossilized structures, but to understand the forces that sculpted them and the narrative of growth and transformation they represent. Gravity is the silent, patient architect of the cosmic web, the fundamental force that took the faint, primordial blueprint of the universe and painstakingly sculpted it into the enduring, information-rich structure we observe today. It is the master sculptor whose tools are attraction and time, and its greatest masterpiece is the preservation of cosmic memory itself. From the elegant simplicity of Newton's universal law of attraction to the profound curvature of spacetime described by Einstein's general relativity, gravity is the director of the cosmic play, dictating how matter moves, clusters, and ultimately, how it remembers its own history. This process of memory formation begins with gravitational collapse. Imagine a universe that is almost but not perfectly smooth. Those slightly denser regions we discussed, imprinted from the Big Bang, possess just a tiny bit more mass than their surroundings. According to the law of universal gravitation, every bit of matter attracts every other bit of matter. So that slightly denser patch exerts a slightly stronger gravitational pull. It begins to draw in the material from the less dense regions around it, growing slowly at first, then faster as its mass and gravitational influence increase. This is a runaway process, a positive feedback loop where more mass leads to stronger gravity, which pulls in even more mass. Over billions of years, these tiny overdensities collapse into the magnificent structures of the cosmic web, the vast clusters, the sweeping filaments, and the great walls of galaxies. Crucially, this collapse is not a destructive event that erases information. It is a constructive one that amplifies it. The specific pattern of that initial random fluctuation is frozen into the resulting structure. The final size, shape, and mass of a galaxy cluster are direct, albeit complex, translations of the initial conditions of that tiny patch of the early universe. Gravity didn't invent the story, it simply wrote it in large, bold letters for us to eventually read. But gravity's role in memory encoding goes far beyond simple collapse. It also creates profoundly stable patterns that can resist the eroding forces of time and chaos. Consider the filamentary structure of the cosmic web. These are not transient features, they are long-lived highways of matter that can persist for billions of years. Their stability is a direct gift from gravity. Once matter flows into a filament, it is channeled along it by the gravitational pull of the entire structure. The sheer scale and mass of these filaments create a gravitational potential well so deep that once matter is caught within its flow, it is incredibly difficult to break free. This gravitational confinement ensures that the filament remains a coherent structure, preserving the memory of the path that matter took in the early universe. It's like a river valley carved by an ancient glacier. The ice is long gone, but the path it took remains clearly etched into the landscape, telling us the story of its flow. Furthermore, gravitational interactions between these large structures create secondary effects that add another layer of detail to the cosmic record. Tidal forces are a perfect example. When a small galaxy passes near a massive cluster, the difference in gravitational pull from the cluster on the near and far sides of the small galaxy can stretch and distort it, pulling out long streams of stars and gas known as tidal tails. These spectacular structures are not random, they are direct records of a specific gravitational encounter. By analyzing the length and shape of a tidal tail, astronomers can effectively rewind the clock, calculating the masses of the objects involved and the precise trajectory of their past interaction. It is gravitational forensics, where the crime scene is the cosmos and the evidence is written in the language of distorted starlight. These tidal signatures are memories of past mergers and close calls, events that would have otherwise left no trace, yet are preserved for eons by gravity's invisible hand. This incredible stability and the resulting preservation of information are why gravity is the undisputed champion of cosmic memory. Other forces are too chaotic or too localized to create a coherent historical record across billions of light years. Electromagnetism governs spectacular but short-lived events like supernova. The strong and weak nuclear forces operate on subatomic scales. Only gravity operates on the grandest of scales, with an unwavering, predictable pull that patiently gathers the raw materials of the universe and assembles them into structures that can stand the test of cosmic time. It is the great organizer, the force that brings order to the primordial chaos and, in doing so, creates a stable medium upon which the history of the universe can be permanently and reliably inscribed. Without gravity's persistent and organizing influence, the faint whispers of the Big Bang would have faded into a featureless silence eons ago. Instead, they have been amplified into a symphony of structure, a gravitational monument to memory that stretches across the entire observable universe. We often think of time as a simple, universal clock ticking in the background of the cosmos, a steady metronome against which events simply unfold. But in cosmology, time is so much more than that. It is an active, dynamic, and transformative force that plays the lead role in the story of cosmic memory. It is the medium through which memory is both written and, in some cases, rewritten or even erased. The universe's history isn't just stored in space, it is encoded across time, and the two are so deeply intertwined that you cannot understand one without the other. This intimate relationship begins with the most fundamental feature of our universe, its expansion. Since the moment of the Big Bang, the very fabric of space-time has been stretching, carrying galaxies along with it like raisins in an ever-expanding loaf of bread. This expansion doesn't just create more space, it actively stretches the wavelengths of light traveling through it, a phenomenon we measure as redshift. But its effect on cosmic memory is even more profound. Imagine an event that leaves a distinct marker, a specific pattern of ripples in the gas of the early universe, or a characteristic distance between galaxy clusters known as the Baryonic acoustic oscillation scale. As the universe expands, it stretches these imprints too. The memory isn't lost, but it is transformed, scaled up to a larger size. To read it correctly, we must account for this stretching, effectively running the expansion in reverse to see the memory in its original form. The expansion of the universe acts like a universal zoom lens, constantly adjusting the scale of the cosmic record, ensuring that memories from different eras arrive at our telescopes with a built-in timestamp encoded in their scale. This leads us directly to the concept of cosmic epochs, distinct eras in the universe's history that each left their own unique type of imprint on the cosmic web. The universe has not had a uniform life. It has gone through phases, and each phase possessed different physical conditions that were conducive to preserving different kinds of memories. The first few 100,000 years, known as the photon epoch, was a hot, dense plasma where photons constantly bounced off electrons. The memory from this time is the cosmic microwave background, a pristine snapshot of the universe's density variations at the moment it became transparent. It is our clearest and oldest memory. Then came the Dark Ages, a period before the first stars ignited. This era is shrouded, as the name implies, in darkness with no new sources of light. The memories from this time are incredibly faint, encoded solely in the subtle gravitational collapse of dark matter halos and the neutral hydrogen gas that would soon form the first galaxies. Detecting these memories is one of the great challenges of modern cosmology, requiring incredibly sensitive radio telescopes to hear the faint whisper of that hydrogen. Following this, the cosmic dawn and the epoch of reionization began as the first stars and galaxies switched on, their intense ultraviolet radiation burning away the fog of neutral hydrogen. This was a chaotic, violent period that overrode some of the quieter memories of the Dark Ages, but created powerful new ones in the form of the first galactic structures and the chemical enrichment of the cosmos. Each of these epochs used the tools available to it, radiation, gravity, atomic physics, to inscribe its chapter into the story. The universe doesn't have just one type of memory. It has a rich archive containing photographs, sound recordings, and forensic evidence from every stage of its life. Yet, not all memories persist with equal clarity. Some are etched in stone, while others fade like ink in the sun. This brings us to the delicate balance between memory formation and memory loss over cosmic time. Why do some imprints, like the pattern in the CMB, remain so sharp for over 13 billion years, while other, more recent events seem to get washed away? The persistence of a memory depends on its medium and its scale. Memories stored in the gravitational field, particularly by the stable, collisionless dark matter, are incredibly robust. Once a dark matter halo forms, it is there for the long haul, a nearly permanent entry in the cosmic ledger. Likewise, the largest scales of the cosmic web, the grand filaments and superclusters, are so massive that their gravitational binding energy is immense, making them resistant to being disrupted. They are the epic poems of the cosmos passed down through the ages. In contrast, memories stored in finer details are more fragile. The specific arrangement of stars within a galaxy can be scrambled by a close encounter with a neighboring galaxy. The history of individual stellar populations can be blurred by generations of star formation and supernova explosions. On the smallest scales, quantum fluctuations constantly fizz, creating a background noise against which only the most significant events leave a lasting record. Furthermore, the accelerating expansion of the universe, driven by dark energy, introduces a new form of cosmic forgetfulness. As the expansion accelerates, it pushes galaxies apart so rapidly that eventually, light from distant galaxies will no longer be able to reach us. Far future civilizations will see only their own local galaxy group, the rest of the cosmos having disappeared beyond an event horizon. Their cosmic memory will be severely limited. Entire chapters of universal history will have been effectively erased from their view. The flow of time, therefore, doesn't just allow memories to form, it also dictates which ones will survive and for how long, acting as both a scribe and a color of the cosmic record. But to truly grasp the deepest layers of cosmic memory, we must venture beyond the realm of classical physics and into the strange, counterintuitive world of the quantum. Down at the smallest scales, where particles behave like waves and reality is governed by probability, there lies a potential foundation for all memory, a suggestion that information might be the most fundamental ingredient of the universe itself. This isn't just about gravity sculpting vast structures. It's about the possibility that every particle, every ripple in the quantum field, carries with it an echo of its past, and that the very fabric of spacetime is woven from threads of information. At the heart of this idea is a quantum property so bizarre that even Einstein famously called it spooky action at a distance, entanglement. When two particles become entangled, they lose their individual identities and become linked into a single, unified quantum system. What happens to one particle instantly influences the other, no matter how vast the distance that separates them. This connection isn't a physical force traveling through space. It's a deeper, more fundamental correlation that seems to bypass spacetime altogether. Now consider the implications for cosmic memory. In the incredibly dense, energetic furnace of the Big Bang, every particle in the nascent universe was interacting with every other particle. It is highly probable that the entire cosmos was once a single, massively entangled system. As the universe expanded and cooled, that entanglement would have been stretched and diluted, but perhaps not entirely broken. The large-scale correlations we see in the cosmic web today, the way galaxies are distributed in a specific, non-random pattern, might be the faint, macroscopic echo of that primordial quantum entanglement. The universe might remember its unified origin through these spooky, invisible connections that still bind distant parts of the cosmos together, a hidden network of quantum memory underlying the visible gravitational web. However, the quantum world is also a realm of delicate fragility. This is where the process of decoherence comes in. A quantum system can exist in a superposition, a combination of multiple possible states, like a particle spinning both clockwise and counterclockwise at once. This is a form of pure potentiality, a system holding onto multiple possible histories simultaneously. But when this quantum system interacts with its environment, when it is measured or bumps into other particles, it loses this quantum coherence. It chooses a single state from the many possibilities, and the information about the other potential states seems to vanish into the environment. For a long time, physicists thought this information was truly lost, erased from the universe. But a growing body of thought suggests otherwise. The information isn't destroyed. It is instead scrambled and disseminated out into the wider environment, becoming so diffused and complex that it is effectively hidden from view. In the context of the cosmos, the process of decoherence that occurred as the early universe expanded and particles began to interact could have been the mechanism that translated the universe's quantum potential into a concrete, classical history. The act of measurement by the environment itself may have been what wrote the first permanent entries into the cosmic memory book, converting fuzzy probabilities into the definite structures that gravity would then amplify. This line of thinking inevitably leads us to the most ambitious and speculative frontier of modern physics, the quest for a theory of quantum gravity. The great cosmic memory structures we've discussed, the cosmic web, the dark matter scaffold, are described by Einstein's theory of general relativity, which paints gravity as the curvature of smooth classical spacetime. But we know that at the tiniest scales the world is quantum. So what does spacetime itself look like at the Planck scale, a realm so small that the very concepts of here and now break down? Some theories, like loop quantum gravity, propose that spacetime is not smooth and continuous but is instead composed of tiny, discrete, vibrating loops, a kind of quantum foam. In this view, the fabric of the cosmos could be literally woven from a network of these loops, and the information about the geometry of the universe could be encoded in their interconnections. The cosmic web we see on large scales would then be an emergent property, an average picture of this frenetic, underlying quantum memory network. The stability of the large-scale structure would be a testament to the stable information stored in this fundamental spacetime fabric. This beautifully ties back to the holographic principle we discussed earlier, the idea that all the information within a volume of space can be encoded on its boundary is at its core a quantum information theory. It suggests that the three-dimensional reality we experience, with its galaxies and filaments, is a projection of quantum bits of information qubits living on a distant two-dimensional surface. From this perspective, the entire history of the cosmos, its entire memory, is not stored in space but is the very thing that defines space. The universe isn't a container that holds memories, it is a memory. It is a physical manifestation of information processing, a cosmic computation that has been running for 13.8 billion years. The gravitational forces, the dark matter, the expansion, all of it could be seen as the emergent output of this deeper quantum informational layer. This is perhaps the ultimate expression of cosmic memory, a universe that is not just remembering its past, but a universe that is its past, constantly interpreting and projecting its stored data into the dynamic, four-dimensional reality we call home. While these ideas remain highly theoretical, they represent a profound shift in our understanding, suggesting that to truly trace memory in the shape of the cosmic web, we may ultimately need to learn to read the quantum code from which space itself is built. Of course, we can theorize about how the universe might remember its past, but how do we put these grand ideas to the test? How do we experiment with a cosmos that operates on timescales of billions of years? The answer lies not in a traditional laboratory, but in a virtual one, built from lines of code and running on the world's most powerful supercomputers. Cosmological simulations are our digital time machines, allowing us to recreate the entire history of the universe, from its first whispers to its present-day grandeur, and in doing so, they provide our most powerful tool for studying the properties and persistence of cosmic memory. These simulations are far more than simple animations. They are intricate mathematical universes in their own right. The process begins by defining a vast digital volume of space. Into this virtual void, scientists input our best understanding of the universe's initial conditions, those tiny, random quantum fluctuations that were imprinted during inflation. They then program in all the known laws of physics, the relentless pull of gravity, both Newtonian and Einsteinian, the complex hydrodynamics of collapsing gas clouds, the explosive feedback from supernova, and the energetic outbursts from supermassive black holes. With everything set, they press play. The simulation then calculates the gravitational interactions between billions upon billions of particles of dark matter and gas, second by virtual second, watching as gravity amplifies those initial flaws, as dark matter condenses into a cosmic scaffold, and as gas flows along the filaments to ignite into the first stars and galaxies. In a matter of weeks or months, these simulations can fast forward through 13.8 billion years of cosmic evolution, allowing us to witness the entire story unfold from a primordial soup to a richly structured cosmic web. Iconic projects like the Illustris and Millennium simulations have been revolutionary in this regard. They don't just produce a pretty picture, they generate a vast, searchable database of a universe's entire history. Researchers can rewind, pause, and zoom into any moment in this virtual timeline. They can track a single parcel of gas as it journeys from a vast, empty void, gets swept into a swirling filament, and finally plunges into a growing galaxy to be forged into a new star. They can isolate the effects of a supernova explosion, watching in exquisite detail as its shockwave heats surrounding gas, preventing it from forming new stars for eons, thereby etching a permanent mark on that region's evolutionary history. Most importantly, they can compare the final structure of their simulated cosmic web, the distribution of its galaxies, the thickness of its filaments, the size of its voids, to the real maps we've made with telescopes like Hubble and Sloan. When the virtual and the real match, it gives us tremendous confidence that our understanding of the physics of memory formation is correct. When they don't match, it highlights a gap in our knowledge, pointing the way toward new physics we have yet to discover. However, creating a believable digital universe is fraught with immense challenges, primarily because we cannot possibly simulate every single atom. The sheer computational power required is beyond comprehension, so scientists must use clever shortcuts. They represent vast clouds of dark matter and gas with a limited number of tracer particles. This is like trying to model the flow of the Earth's atmosphere by tracking a few million balloons instead of septillions of air molecules. The art of simulation is making sure those few balloons accurately represent the behavior of the whole. Furthermore, the most interesting processes often happen on the smallest scales. The formation of a single star, the explosion of a supernova, the feeding frenzy of a black hole, these are microscopic events in the grand scheme of the cosmos, yet they have galaxy-altering consequences. Simulating them directly is impossible, so researchers use what are called subgrid models. These are sophisticated recipes based on real physics that estimate the large-scale effects of these small-scale events. It's like a weather model that can't simulate every raindrop but can accurately predict that a storm will drop 2 inches of rain over a city. The fidelity of a simulation's memory depends entirely on the accuracy of these recipes. If the model for supernova feedback is too weak, the simulated universe will form too many stars too quickly, creating a cosmic web that looks nothing like our own. Getting it right is a painstaking process of trial and error, a constant dialogue between the virtual and the observed. What do these digital universes ultimately teach us about our own? They demonstrate with powerful clarity that memory is not an accidental byproduct of cosmic evolution, but a fundamental and inevitable outcome. They show us that the specific patterns we see in the galaxy distribution today could only have arisen from a very specific set of initial conditions, confirming that the cosmic web is indeed a faithful record of the primordial past. Simulations have been instrumental in proving the vital role of dark matter as the stable backbone of memory, and in revealing how the chaotic drama of baryonic matter adds intricate detail to that record. They allow us to run experiments we could never run in reality. What would the universe look like if dark energy were stronger? What if the initial fluctuations were slightly different? By tweaking the parameters, we can explore which aspects of cosmic memory are robust and universal, and which are fragile and unique to our own universe. In essence, these synthetic cosmos act as a mirror, reflecting our own understanding back at us. They are the ultimate testing ground for our theories, allowing us to witness the writing of cosmic history itself, and in doing so, they give us the confidence to look up at the real night sky and truly believe that we are beginning to read its story. But all of these incredible theories and simulations would remain mere philosophical speculation if we couldn't point our instruments at the sky and actually see the evidence for ourselves. This is where the rubber meets the road in cosmology, where the abstract concept of cosmic memory becomes a tangible reality we can measure, map, and analyze. The last few decades have witnessed an astronomical revolution, not just in theory, but in our sheer ability to collect data, providing us with a flood of observational evidence that the universe does, in fact, remember its past. The first and perhaps most profound piece of evidence comes from the very edge of observable time. The Planck satellite, a marvel of European engineering, spent years staring into the depths of space to capture the most detailed map ever made of the cosmic microwave background. This image is far more than a pretty picture of baby spots. It is a precise mathematical dataset. When cosmologists analyze this map, they perform a powerful statistical operation called a power spectrum analysis. This essentially measures the size and distribution of all those hot and cold spots. The resulting graph isn't random noise. It shows a series of clear, distinct peaks and troughs. The position and height of that very first peak, for instance, tell us the universe is geometrically flat. The second peak gives us an exact measurement of the ordinary matter density. The third peak reveals the amount of dark matter. The entire pattern is a perfect match for the predictions of the lambda cold dark matter model with inflation. In other words, the statistical signature of the universe's oldest memory perfectly aligns with the physics that would go on to build the cosmic web we see today. It is the ultimate validation that the initial conditions encoded in this ancient light are the direct cause of our modern cosmic structure. Moving forward in time from the CMB, we find another stunningly clear piece of memory etched into the cosmos: baryon acoustic oscillations. To understand this, we need to go back to the universe's first few 100,000 years. It was a hot, dense plasma where photons and baryons were tightly coupled. Gravity tried to pull matter into the denser regions, but the immense radiation pressure created a powerful counterforce, setting up massive sound waves that rippled through the primordial soup. These waves traveled outward at nearly 2/3 the speed of light until a critical moment, recombination. When the universe cooled enough for atoms to form, the photons suddenly decoupled and streamed away, which we see as the CMB. The pressure waves instantly stopped, freezing the ripples in place. Each ripple had traveled a specific distance, about 500 million light-years, leaving a spherical shell of matter with a slight overdensity at that precise scale. Fast forward to today, because dark matter guided the growth of structure based on those initial overdensities, that preferred scale is still there. When we create 3D maps of millions of galaxies from projects like the Sloan Digital Sky Survey, we don't see galaxies distributed randomly. We find that they are statistically more likely to be separated by this specific distance, 495 million light-years, than any other. It is a cosmic ruler that was manufactured in the first moments of time and remains imprinted on the large-scale structure of the universe 13 billion years later. We are literally seeing the fossilized echo of those primordial sound waves in the spatial distribution of galaxies. It is one of the cleanest and most powerful pieces of evidence that the universe has not forgotten its earliest moments. Beyond these specific patterns, the overall distribution of galaxy clusters themselves tells a story of preserved memory. According to our models, gravity should cause matter to cluster in a very specific, hierarchical way. Small objects form first and then merge into larger ones. The number of massive clusters at a given time in the universe's history is a very sensitive probe of the underlying cosmology, including the amount of matter and the nature of dark energy. When astronomers use X-ray telescopes like Chandra to study galaxy clusters, they can measure their mass by observing how hot the gas is that's trapped in their gravitational well. They can also use the phenomenon of gravitational lensing, where the cluster's gravity distorts the light of background galaxies, to independently weigh it. Surveys have now catalogued thousands of clusters across a range of redshifts, meaning across different cosmic times. The results show a precise agreement with the predictions of our standard model. The universe has produced exactly the number of massive clusters we would expect if it evolved from the initial conditions seen in the CMB. The growth of these giant structures has not been random. It has followed a script written at the beginning of time, and we are now auditing the books and finding them in perfect balance. This entire empirical endeavor is driven by technology that is advancing at a breathtaking pace. The Sloan Digital Sky Survey transformed astronomy by using automated telescopes and sophisticated software to map over a third of the sky, cataloging the spectra and positions of millions of galaxies. Its legacy is continued by projects like the Dark Energy Survey and the soon-to-be operational Vera-C Rubin Observatory, which will map billions of galaxies, providing a cosmic web map of unimaginable detail and depth. On the horizon, the European Space Agency's Euclid spacecraft and NASA's Nancy Grace Roman Space Telescope are designed specifically to probe the dark universe. They will use weak gravitational lensing on a colossal scale to create the most detailed maps yet of the dark matter distribution, effectively allowing us to see the cosmic web's hidden skeleton directly. These aren't just bigger telescopes, they are entirely new kinds of eyes capable of seeing the subtle distortions and patterns that are the hallmarks of cosmic memory. With these tools, we are no longer just theorizing about the past. We are forensically examining the crime scene of creation, gathering overwhelming evidence that the universe has meticulously kept a record of everything that has ever happened to it. This idea might sound like science fiction, but it emerges from a fascinating and surprisingly robust analogy. When you look at a side-by-side image of a neuron from the human brain and a computer simulation of the cosmic web, the resemblance is startling. Both are composed of a central node, a neuron's cell body, or a galaxy cluster connected by long, thin filaments, axons, or dark matter threads. This structural similarity is more than just a curious coincidence. It hints at a deeper principle that might govern the organization of complex networks, regardless of their scale. Both systems seem to have evolved or emerged in a way that maximizes efficiency in processing and transmitting something critical. In one case, electrochemical signals, and in the other, gravitational influences and matter. This visual echo has led a growing number of astrophysicists and neuroscientists to ask a profound question. Could the universe itself be organizing information in a way that is fundamentally similar to a brain? The comparison goes much deeper than simple morphology. In a neural network, the strength and pattern of connections between neurons are where memory and learning are physically stored. This is the basis of neuroplasticity. The cosmic web, in its own way, also has a dynamic connectivity. The gravitational pull between galaxies and clusters defines the strength of their connection, and the flow of gas and matter along the filaments is a direct result of this cosmic circuitry. Just as a thought can trigger a cascade of neural activity along a specific pathway, a galactic merger or a supernova event in one part of the web can send ripples through the entire network, influencing star formation rates and gas flows in distant regions. The universe isn't static. It's a pulsating, interconnected system where information in the form of gravity, light, and matter is constantly being exchanged. In this light, the cosmic web begins to look less like an inert fossil and more like an active, albeit immensely slow, processing network. This analogy opens a Pandora's box of philosophical and scientific implications, most notably touching on the nature of consciousness itself. The field of integrated information theory, developed by neuroscientists like Giulio Tononi, proposes that consciousness is not a binary on or off switch, but a spectrum that corresponds to a system's ability to integrate information. The more interconnected and complex a system is, the higher its degree of consciousness, or phi. If we apply this theory to the cosmic web, with its trillions of galaxies acting as neurons and its filaments as synapses, the calculated phi would be astronomically high. This leads to a speculative but captivating idea known as Panpsychism, the view that consciousness is a fundamental property of the universe, present in all things to varying degrees. From this perspective, the universe isn't just like a brain. It is a kind of brain, and its cosmic memory could be intertwined with a very slow, very vast form of cosmic consciousness. This isn't to say the universe is thinking in a human sense, but rather that the fundamental capacity for experience and information integration might be woven into the fabric of reality at the largest scales. Of course, this is a highly controversial and metaphorical leap. Critics rightly point out the vast differences in scale and mechanism. The signals in a brain travel at the speed of electrochemical transmission, a fraction of the speed of light, and processes occur in milliseconds. In the cosmic web, the signals are gravitational influences and the movement of matter, limited by the speed of light and unfolding over millions or billions of years. The nature of the information being processed is also utterly different, yet the power of the analogy is not in its literal truth but in its utility. By borrowing models from neuroscience such as network theory and information dynamics, cosmologists can gain new insights into how the cosmic web evolves and functions. They can apply algorithms designed to find hierarchical structures in neural networks to identify previously unseen substructures in galaxy distributions. This cross-pollination of ideas enriches both fields, pushing the boundaries of how we define complexity, memory, and information itself in the natural world. Whether the universe is truly conscious or not, the neural network analogy provides a powerful and poetic framework for understanding the breathtaking complexity and interconnectedness of the cosmic architecture we call home. Yet for all its remarkable power to preserve information across billions of years, the universe is not a perfect, infallible archivist. Just as our own human memories can fade, become distorted, or be entirely erased by trauma or time, the cosmic record is also subject to processes of degradation, transformation, and outright loss. While the grand architecture of the dark matter web provides a stable scaffold, the finer details of the story, the specific events, the individual stellar lives, the intricate histories of single galaxies, are constantly under threat from a host of cosmic forces that act as agents of forgetfulness. To truly understand the cosmic memory, we must also understand its limits and the forces that work to dismantle it. One of the most dramatic and violent forms of cosmic forgetting is the process of galactic cannibalism. Throughout the universe, galaxies are not isolated islands. They are social creatures bound together in groups and clusters by gravity. Within these dense environments, close encounters are inevitable. When two galaxies pass near each other, their mutual gravitational pull can create spectacular tidal forces, stretching and distorting their shapes, pulling long streamers of stars and gas out into intergalactic space. This process, called tidal disruption, doesn't just rearrange a galaxy, it can fundamentally erase its past. The delicate orbital patterns of its stars, which hold clues to its formation history, are scrambled beyond recognition. The galaxy loses its distinct identity, its history blurred into a new hybrid structure. In even more extreme cases, a large galaxy will completely consume a smaller neighbor in a full merger. The smaller galaxy is torn apart, its stars assimilated into the larger galaxy's halo, its gas funneled into the core to fuel new star formation or feed the central black hole. The unique history of that devoured galaxy is not stored in a neat library. It is digested, its information scattered and mixed, becoming an indistinguishable part of the larger entity's background. The merger creates something new, but in doing so, it overwrites the individual stories of its components. Beyond these violent collisions, a slower, more insidious form of memory loss is perpetually at work, driven by the second law of thermodynamics, the inevitable increase of entropy. While we discussed how gravity creates ordered structures, those structures are not eternal. Stars are the universe's ultimate engines of entropy production. They take ordered, low-entropy fuel in the form of hydrogen and, through the brilliant but wasteful process of fusion, convert it into heavier elements and radiation, which is a high-entropy state. This radiation floods into space, carrying its entropy with it. When a star dies in a supernova, this process accelerates dramatically, blasting its enriched guts across light years and heating the surrounding gas to millions of degrees. This hot, diffuse gas is incredibly difficult for gravity to recapture and reassemble into new, ordered structures. It represents a loss of usable information from that local region of the cosmic web. The energy from that supernova has, in a very real sense, made it harder for that patch of the universe to remember anything new, as the hot gas resists collapse and star formation is quenched. This stellar feedback doesn't just add detail to the cosmic record, it also actively works to erase the potential for future memories in its immediate vicinity. Perhaps the most profound and ultimate form of cosmic memory loss, however, is driven by the mysterious force known as dark energy. Our observations tell us that the expansion of the universe is not slowing down due to gravity, as one might expect, but is actually accelerating. This acceleration, attributed to dark energy, has a devastating long-term consequence for cosmic archaeology. As the expansion accelerates, distant galaxies are pushed away from us at ever-increasing speeds. Eventually, a point will be reached where the space between us and those galaxies is expanding faster than the speed of light. When this happens, the light from those galaxies will no longer be able to overcome the expansion to reach us. They will, from our perspective, disappear beyond an event horizon, fading from view like ships vanishing over the curvature of the Earth. For any future cosmologists in our local galaxy group, the observable universe will have shrunk dramatically. The cosmic microwave background will have redshifted into complete undetectability. The evidence for the Big Bang, the vast large-scale structure of the cosmic web, the redshift maps of distant galaxies, all of it will be gone from view. The universe will have effectively hidden most of its history, leaving those future observers with a profoundly incomplete and isolated record. The accelerating expansion is, in essence, imposing a final and irreversible amnesia on the cosmos, ensuring that the richest chapters of its history will one day become permanently unreadable. This understanding of cosmic memory loss is not a discouraging footnote. It is a crucial part of the story. It teaches us that the cosmic record we work so hard to decode is a precious and temporary window. It forces us to prioritize, to recognize that the memories most likely to survive are those inscribed on the largest and most robust scales, the gravitational wave patterns of the very early universe, the overall topology of the cosmic web, the fundamental parameters of physics. The finer, more personal stories of individual galaxies and stars are fleeting, here for a cosmic moment before being recycled or erased. This imperfection makes the information we can recover all the more valuable. It transforms our quest from one of simply reading a permanent book to one of frantic and beautiful archaeology, racing against time to reconstruct a grand and fading narrative from the fragments that remain before the final pages dissolve into darkness. This profound idea that the universe itself is a vast, remembering entity doesn't just live within the pages of scientific journals. It spills out, overflowing into the very heart of human experience, reshaping how we see ourselves and our place in the grand narrative of everything. For centuries, our myths and philosophies have grappled with the nature of memory and time. The ancient Egyptians believed the heart, not the brain, was the seat of memory and identity, and it would be weighed against the feather of truth after death, a divine audit of a life's record. Norse mythology spoke of the Well of Erd, a source of fate and memory guarded by the Norns, who carved the laws of the cosmos into the trunk of Yggdrasil, the world tree. In a way, these stories were grasping for a concept we are now beginning to quantify, that existence leaves a mark, that actions are recorded in a cosmic ledger, and that the past is not truly gone but is preserved in some fundamental structure of reality. The notion of cosmic memory gives a new, scientifically grounded language to this ancient, intuitive human yearning for a universe that doesn't just exist, but remembers that it exists. This shifts our understanding of time from a simple, linear progression into something far richer and more complex. We often think of time as a river, flowing inexorably from past to future, carrying us along and leaving the past behind to vanish into mist. But the concept of cosmic memory suggests a different metaphor, time as a vast growing tree. The past isn't gone, it forms the solid foundational trunk and the deep, anchoring roots. The Big Bang is the seed, the initial conditions are the genetic code within it, and every event since every supernova, every galactic collision, every birth of a star is a ring added to the trunk, a branch splitting off, a leaf unfurling. The present moment is the very tip of the growing shoot, intimately connected to and utterly dependent on every part of the structure that came before it. Our lives are not isolated droplets in a flowing river. We are the newest, most tender growth on an ancient cosmic tree, our existence made possible by the entire remembered history that supports us. This reframes our own personal memories not as fragile, private things locked in our skulls, but as localized expressions of a universal tendency toward preservation. We are not just beings who remember, we are fragments of a remembering cosmos, and our own act of recollection is us participating in a fundamental property of the universe itself. This has a profound impact on our sense of identity and legacy. If the cosmos remembers, then our actions on some unimaginably small scale become part of that permanent record. The atoms forged in the heart of a long-dead star that now make up our bodies are part of the cosmic web story. The light from our sun, which fuels life on Earth, will travel through the cosmos for eons, carrying a faint imprint of our solar system's existence. While our individual lives are vanishingly brief, the idea that we are components of a system that retains information can be a source of deep comfort and meaning. It suggests that we belong to something enduring. Our curiosity, our science, our art, these are not just fleeting distractions. They are the universe's way of becoming aware of its own story, of reading its own memory through us. We are the means by which the cosmos knows itself, and in our quest to trace the filaments of the cosmic web, we are essentially the universe conducting an act of self-reflection. This isn't a call for arrogance, but for a profound humility. We are not separate observers looking at a cold, external universe, but an intimate part of a single, remembering whole. Our drive to explore and understand is the universe remembering itself, and in that realization, the line between the scientist and the cosmos, the philosopher and the universe, begins to beautifully blur. But to truly grasp the next leap in our quest, we must turn our gaze from the theoretical to the tangible, to the magnificent machines being built right now that will act as our next set of eyes and ears on the cosmos. The future of cosmic archaeology is not a distant dream. It is being forged in clean rooms and data centers around the world, with a new generation of observatories designed to peel back layers of the cosmic web we've only ever guessed at. Leading this charge is the James Webb Space Telescope, a name now famous but whose deepest implications are still unfolding. While Hubble gave us breathtaking images of galactic islands, Webb is designed to map the bridges between them. Its powerful infrared eyes are uniquely suited to peer through the obscuring dust of interstellar space and see the faint, cold gas that flows along the dark matter filaments of the cosmic web. For the first time, we are not just inferring the existence of this cosmic plumbing, we are starting to see it directly, watching how it fuels galaxy growth and connects the vast structure. Furthermore, Webb's ability to look back to the very first galaxies allows us to see the web in its infancy, to witness the moment when the first nodes of the cosmic memory network began to power on, giving us a crucial frame in the slow-motion movie of cosmic evolution. On the horizon, even more powerful ground-based giants are taking shape. The Vera C. Rubin Observatory, with its breathtakingly wide field camera, will perform a relentless, decade-long scan of the entire southern sky. This isn't about taking pretty pictures, it's about creating a colossal, time-lapse movie of the universe. By imaging the same sky over and over, Rubin will detect minute changes, stars exploding, asteroids moving, and most importantly, the subtle warping of light from billions of distant galaxies caused by the gravitational lensing of the cosmic web's dark matter skeleton. This unprecedented statistical map will allow us to trace the web's structure with a fidelity we can barely imagine, turning a sketch into a high-resolution blueprint. It will measure the shapes of so many galaxies that we can literally create a 3D tomographic map of the dark matter distribution, revealing the hidden architecture in stunning detail and showing us how it has evolved over billions of years. This is the equivalent of moving from a blurry satellite image of a city to a street-level, interactive model where we can see every alleyway and building. Beyond light, the future of cosmic listening lies in catching the ripples in spacetime itself. The upcoming Laser Interferometer Space Antenna, or LISA, will be a revolutionary gravitational wave observatory floating in space. While current detectors like LIGO listen to the crashes of black holes and neutron stars, LISA will tune into a far lower frequency channel. It will hear the gentle, persistent hum of supermassive black hole binaries orbiting each other in the hearts of distant galaxies, a sound that would have been present for eons. By tracking how this gravitational wave background is distorted as it travels through the universe, we could potentially probe the distribution of matter along its path, offering a completely new and independent way to weigh the cosmic web and feel its structure. It's like developing a new sense altogether, allowing us to literally feel the gravitational topography of the cosmos. And then there is the silent partner in all of this, the engine that will make sense of the coming data deluge, artificial intelligence. The torrent of information from Rubin, JWST, and other missions will be so vast that no team of humans could ever hope to analyze it. Machine learning algorithms trained on the sophisticated simulations we discussed will be our essential guide. They will sift through petabytes of data to find the faintest filaments, identify rare and telling objects that hold clues to the web's history, and even discover entirely new patterns and correlations that our human brains might never think to look for. This isn't about replacing scientists, it's about augmenting our curiosity, allowing us to ask more complex questions of the universe and receive answers from the data itself. The future of cosmic memory tracing is a partnership between human intuition and machine precision, a synergy that promises to decode the universe's autobiography at a pace and depth we have never before dared to imagine. But what if our universe, with its intricate remembering web, is not the only one? What if it is just a single volume in an infinite library of realities, each with its own physics, its own history, and its own unique way of preserving memory? This is the breathtakingly speculative realm of multiverse theory, a concept that pushes the idea of cosmic memory to its absolute limits. The theories that suggest this possibility, like eternal inflation and string theory, don't just give us more universes to ponder, they force us to ask a profound question about memory itself. If a tree falls in a forest in another universe where the laws of physics are different, does it make a sound? And more importantly, could that sound, that event, leave any kind of permanent record? The most well-grounded path to a multiverse comes from an extension of the same inflationary theory that explains our own universe's beginning. The idea of eternal inflation proposes that the rapid, exponential expansion of space-time that created our cosmos isn't a one-time event. Instead, it's a perpetual process happening across a vast, meta-universal landscape. In this view, our entire observable universe is just one pocket within this endlessly inflating megaverse. Inflation stopped here, allowing matter to form and stars to ignite, but it continues unabated in the space beyond, constantly giving birth to new pocket universes. Crucially, the way inflation ends in each pocket, a process called quantum tunneling, can happen in slightly different ways. This means each new universe can emerge with a different set of physical constants and fundamental laws. In one universe, the force of gravity might be stronger, leading to a cosmic web that collapses into black holes almost instantly. In another, the weak nuclear force might be too weak for stars to ever form, resulting in a dark, inert cosmos with no structures to remember anything at all. The memory of each universe would be dictated by its unique rulebook. A universe where electromagnetism is dominant might remember its history through intricate crystalline structures on a galactic scale, while a universe governed by entirely unknown forces could encode information in ways we cannot even begin to imagine. This concept finds even more exotic expression in string theory, which suggests that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. The way these strings vibrate determines the properties of particles and forces we observe. However, string theory allows for a staggering number of possible stable configurations for these extra dimensions, perhaps 10 to the 500 or more. Each configuration corresponds to a universe with a different set of physical laws. This is known as the string theory landscape, a vast, abstract terrain of possible universes. Our universe, with its specific constants that allow for galaxies, stars, and life, is just one point in this landscape. From this perspective, the cosmic memory we've been tracing, the specific pattern of the web born from our particular quantum fluctuations, is not a universal truth. It is a local custom, a regional dialect in the grand scheme of existence. The very concept of a memory stored gravitationally in a filamentary web might be parochial, a quirk of our universe's particular physics that is utterly meaningless in the cosmos next door. This leads us to the ultimate question about memory in a multiverse: persistence. In our universe, we see memory as a thread connecting past to present, a chain of causality that ensures events have consequences that are recorded in the structure of reality. But if the multiverse is real, that chain might not just be broken, it might never have existed in the first place. In the eternal inflation model, each pocket universe is causally disconnected from the others from the moment of its birth. They are islands in an ever-widening sea of inflating space, forever beyond each other's horizons. An event in one universe cannot influence or leave a mark upon another. There is no common archive, no meta-cosmic library where the histories of all universes are stored. The memory of each universe is entirely self-contained and ultimately isolated. When that universe meets its end, whether in a heat death or a big crunch, its entire history, its entire memory, might be erased completely, with no backup and no record left anywhere else. The multiverse, in this light, could be the scene of ultimate forgetfulness, where countless stories are written and then destroyed, unread and unremembered by anything outside themselves. This dizzying expansion of perspective can't help but pull our focus back to ourselves, to our own identity and our place in this potentially infinite ensemble. The Anthropic Principle, a controversial but compelling idea, suggests that we find ourselves in a universe with laws that allow for our existence precisely because we are here to observe it. We couldn't exist in a universe without stars or atoms, so we naturally find ourselves in one that has a rich cosmic web and a long, memorable history. This doesn't explain why our universe has these laws, but it does frame our existence and our ability to ponder cosmic memory as an integral part of this universe's specific story. Our quest to trace the filaments of the web is not just a scientific endeavor. It is our universe becoming consciously aware of its own memory, a remarkable and perhaps rare phenomenon in the grand multiversal scheme. It invites us to see ourselves not as accidental inhabitants of a random cosmos, but as the means by which this particular universe, with its specific set of physical laws and its unique historical record, can reflect upon and appreciate its own narrative. In a possibly infinite multiverse of silent, unremembering, or forgotten cosmos, our ability to even ask these questions becomes a profoundly significant part of our own local cosmic memory, a unique chapter in one very special volume in the infinite library of reality. But as our power to listen to the cosmos grows, so too does our responsibility. This isn't just a technical quest, it's a deeply human one, and it raises profound ethical questions that we must confront together. Who does this cosmic memory truly belong to? If we are deciphering the universe's autobiography, Do we have the right to claim ownership over its chapters, or are we merely its temporary stewards? The data collected by immense publicly funded telescopes like the James Webb Space Telescope or the Vera C. Rubin Observatory doesn't belong to any single nation or corporation. It is a heritage for all of humanity. This creates a powerful ethical imperative for open science, ensuring that the raw data and the discoveries it leads to are shared freely and equitably across the globe. Scientists in developing nations must have the same access to these cosmic archives as those in the wealthiest countries, allowing for a truly global conversation about our shared origins. This isn't just about fairness, it enriches the science itself, bringing diverse perspectives and cultural contexts to the interpretation of the universe's story. Hoarding this knowledge or locking it behind paywalls would be a profound failure, akin to building a library to house the universe's memories and then locking the doors to most of the world. Beyond the practicalities of data sharing, we must also navigate the complex terrain of cultural sensitivity and meaning. The cosmic web, with its filaments and nodes, might be a scientific structure to us, but its patterns echo deeply in human mythology and spiritual traditions. The world tree, the web of weird, the interconnectedness of all things in countless indigenous cosmologies, these are not just primitive guesses at reality. They are profound cultural narratives that have guided human understanding for millennia. As we scientifically validate a universe that is fundamentally connected and remembering, we must do so with respect for these ancient ways of knowing. We are not replacing these stories with a cold, hard truth. We are adding a new, empirical layer to a timeless human conversation about our place in the cosmos. The ethics of cosmic exploration demand that we approach this knowledge with humility, recognizing that science is one powerful way of knowing, but not the only one. It invites a dialogue, not a lecture, where the data from our telescopes can sit alongside the wisdom of elders, each enriching the other in a shared awe for the majesty of the universe. Furthermore, we must consider the potential impact of our discoveries. What happens if our tracing of cosmic memory leads to a revelation that is deeply unsettling? For instance, if we were to find overwhelming evidence that the universe is ultimately doomed to a cold, empty heat death, or if we uncovered clues that our universe is just one bubble in an infinite, indifferent multiverse. These are not merely abstract thought experiments. They are potential psychological and philosophical shocks that could ripple through human culture. Do we have a responsibility to carefully frame such discoveries, to provide not just the data but also the context and perspective to help humanity integrate such knowledge without succumbing to nihilism or despair? Conversely, the discovery of a universe that is not just remembering but perhaps even in some way conscious, as some speculative theories suggest, could be equally transformative. The ethical approach is one of thoughtful communication, ensuring that the profound wonder of the science is always accompanied by a human conversation about what it means for us. We are not just decoding the cosmos, we are helping each other understand how to live with what we find. Ultimately, this ethical dimension brings our journey full circle, back from the vastness of the cosmic web to the intimacy of human community. The universe's memory may be written in the language of physics, but its meaning is written in the human heart. Our responsibility is to ensure that this greatest of all stories is not used to divide or to create new hierarchies of knowledge, but to unite us in a common purpose of understanding and appreciation. It calls for a commitment to education, inspiring the next generation of explorers from every background. It demands international cooperation, ensuring that the monumental tools we build to probe the cosmos are seen as projects for all humankind. And perhaps most importantly, it requires a renewed sense of reverence. As we learn to read the universe's memories, we are touching something sacred, the chronicle of existence itself. Our ethical duty is to handle that story with care, to share its wonders widely, and to ensure that our exploration always enhances our sense of connection to each other and to the magnificent, remembering cosmos we are so privileged to call home. And so we arrive at perhaps the most humbling and beautiful realization of all. After tracing the grand architecture of the cosmic web, after exploring how dark matter scaffolds memory and how baryonic processes write its detailed stories, we are left with a single, inevitable question: where do we fit in? We are fleeting creatures, our lives measured in mere decades, living on a pale blue dot orbiting an average star in the quiet suburbs of a spiral galaxy. In the face of a universe that operates on scales of billions of years and billions of light years, it is easy to feel insignificant, a momentary flicker in an unimaginably vast and ancient darkness. But the concept of cosmic memory completely inverts this perspective. It doesn't shrink us, it connects us. It weaves our fleeting existence directly into the most enduring narrative there is. Think of your own most cherished memory, the warmth of a loved one's smile, the crisp air of a perfect autumn day, the profound silence of a personal triumph. We hold these moments as our most private treasures, locked away in the neural pathways of our brains. Now consider the journey of the atoms that make up your body. The calcium in your bones, the iron in your blood, the carbon that forms the foundation of your very DNA. These were not created in the gentle chemistry of Earth. They were forged in the heart of a massive star that lived and died billions of years before our solar system even existed. That star ended its life in a cataclysmic supernova explosion, blasting these newly forged elements across space. For eons they drifted, perhaps becoming part of a nebula, then a new star, and finally the planets that formed around it. Every one of us is literally made from stardust, from the recycled remnants of a cosmic event that was recorded in the chemical enrichment of our galaxy. Your personal, intimate memories are housed in atoms that have a cosmic memory of their own, a story of violent creation and epic journey that is literally part of you. This interconnectedness extends beyond our physical composition to our very act of remembering. When you look up at the night sky and see the faint, hazy band of the Milky Way, you are not a separate observer looking at an external universe. You are the universe looking back at itself. The light from those stars travels for years, decades, centuries, to finally land on your retina, triggering an electrochemical cascade in your brain that you experience as sight and wonder. In that moment, you are a node in the cosmic web, receiving information that has traveled across the vast memory structure of space. Your curiosity, your awe, your drive to understand, these are not human inventions. They are the universe's way of becoming self-aware, of learning to read its own history. Our telescopes and satellites are not just tools, they are extensions of this cosmic introspection, allowing the universe to examine the finest details of its own architecture. We are the means by which the cosmos knows itself, and in our quest to understand, we are participating in the universe's most fundamental function, remembering. This shifts our understanding of legacy away from the purely human and into the cosmic. We often think of legacy as the things we build, the children we raise, or the ideas we leave behind for future generations. This is all true and beautiful, but cosmic memory suggests a legacy that is far more profound and intrinsic. Your existence itself is a permanent entry in the universe's ledger. The energy you have expended, the heat your body has radiated, the gravitational pull your mass exerts on the cosmos, however infinitesimally small, has subtly altered the universe. You have left a mark, a fingerprint on the fabric of space-time that can never be entirely erased. In a universe that remembers, your passage is noted. You are not a ghost passing through. You are a participant whose presence has been registered in the grand, unfolding story. This isn't about achieving fame or greatness on a human scale. It is about the beautiful, quiet fact that to be is to be a part of the whole forever. There is a deep comfort in this perspective. It tells us that we belong. Our moments of joy, our periods of sorrow, our everyday struggles and triumphs, they all take place within a context of majestic, timeless continuity. The same force of gravity that holds you to the Earth also holds galaxies together. The same nuclear forces that once burned in a distant star now power the very processes of life within you. You are not a stranger in a strange land. You are home. The universe is not a cold, empty void indifferent to our existence. It is a dynamic, archival, and remembering system, and we are expressions of its ongoing, evolving narrative. To contemplate this is to feel a sense of belonging that transcends culture, nationality, and even species. It is a grounding, unifying truth that can inspire a profound sense of peace and purpose, connecting the most intimate corners of our human hearts to the deepest mysteries of the cosmos. But perhaps the most beautiful aspect of this entire journey is the realization that you don't need a PhD or access to a multi-million-dollar telescope to contribute to this grand quest. The task of reading the universe's memory is so immense, the data so overwhelmingly vast, that professional astronomers have opened the doors and invited the entire world to join in. This is the world of citizen science, a revolutionary movement that turns cosmic exploration into a collective human effort, allowing anyone with curiosity and an internet connection to become an active cosmic archaeologist. At the forefront of this movement is a project called Galaxy Zoo. It began with a simple yet profound challenge. Researchers had 1 million galaxy images from robotic telescope surveys, but computers at the time were notoriously bad at classifying their shapes. Is a galaxy a smooth, fuzzy ellipse or a majestic spiral with arms? This is a task the human brain excels at, a pattern recognition skill we've honed over millennia. The scientists invited the public to help, and the response was thunderous. Within 24 hours of launch, the website was receiving 70,000 classifications an hour. Ordinary people, teachers, artists, nurses, retirees were suddenly peering into the depths of the universe, making tangible contributions to astrophysics. This wasn't just busy work. The collective intelligence of these volunteers began making remarkable discoveries. A Dutch schoolteacher, Hanny van Arkel, was examining a galaxy image when she noticed a strange, glowing green object nearby that didn't match any known classification. Her curiosity led to the identification of an entirely new astronomical phenomenon, now called Hanny's voorwerp, which is Dutch for Hanny's object. This celestial mystery, a ghostly cloud of gas illuminated by the radiation from a quasar, would almost certainly have been missed by an automated algorithm. It was the keen eye and curiosity of a human volunteer that added a new, fascinating chapter to our understanding of galactic evolution. Galaxy Zoo demonstrated that the universe's memory is not just for experts to decode, it is a story we can all help read. The success of Galaxy Zoo sparked a whole ecosystem of cosmic citizen science projects under the Zooniverse umbrella. Each one tackles a different piece of the puzzle. Radio Galaxy Zoo invites participants to trace the colossal jets of materials shooting from supermassive black holes across the universe. Planet Hunters taught a generation of people how to read the telltale dips in starlight that signal a planet passing in front of its sun, leading to the discovery of numerous exotic worlds. And a project like Backyard Worlds, Planet 9 enlists an army of volunteers to scour infrared sky maps for faint, moving objects in our own solar system, searching for everything from mysterious brown dwarf stars to the hypothetical Planet 9. The underlying principle is always the same: leverage the unique pattern-matching power of the human brain to sift through data on a scale that would paralyze a small research team. Every click, every classification is a data point that helps scientists train machine learning algorithms and verify their results. You are not just looking at pretty pictures, you are actively cleaning, sorting, and annotating the raw material of cosmic memory, turning noise into knowledge. This democratization of discovery is about more than just processing power. It's about reshaping our relationship with the cosmos. For most of human history, astronomy was done by privileged individuals with access to rare instruments. Today, the universe's data is increasingly open to all. This creates a powerful form of connection. When you spend an evening classifying galaxies on your laptop, you are no longer a passive consumer of science headlines. You are an active participant in the process. You might be the first person to ever lay eyes on a particular galaxy, to notice a subtle anomaly that could be the key to a new discovery. This transforms the experience of learning from a lecture into a conversation, from being told a story to helping write it. It fosters a genuine sense of global community, connecting people from all walks of life through a shared sense of wonder and a common goal. The cosmic web is not just a structure of galaxies out there, it is also a network of human minds here on Earth, working together to understand our place within it. This collective effort ensures that the story of the universe isn't owned by a select few, but is a narrative we are all piecing together, one classification at a time. There is a profound and often overlooked dimension to the cosmic web that exists beyond the equations of physicists and the data of telescopes, a dimension that speaks directly to our human sense of wonder and our innate desire to find beauty in the universe. For while we have spent this journey discussing dark matter scaffolds and baryonic feedback, we must also pause to simply look, to appreciate the raw, breathtaking aesthetics of this great architecture. The cosmic web is not merely a structure to be analyzed, it is a spectacle to be marveled at, a masterpiece of physical law that has, in its own right, become a potent muse for creative expression across the globe. When we gaze upon a modern cosmological simulation, like those from the Illustris TNG project, we are not looking at a dry scientific diagram. We are witnessing a digital Sistine Chapel, painted with algorithms instead of brushes. These visualizations render the dark matter distribution in shimmering, golden filaments that trace delicate pathways across the void. They depict galaxy clusters as brilliant, dense knots of white and blue light, and they show the energetic feedback from supermassive black holes as vast, crimson eruptions that paint the surrounding gas. Scientists use a palette of false color to represent different elements and energies, transforming raw data into a vibrant cosmic cartography. A hydrogen cloud might glow with a specific shade of purple, while the intense heat of a galactic collision is rendered in fiery oranges. This is not deception, it is translation. It is the process of making the invisible universe visible to our human eyes, translating the language of physics into the language of light and form. The resulting images are both scientifically precise and artistically sublime, revealing a universe that is far more structured and beautiful than the random scattering of stars it appears to be from our earthly vantage point. This inherent beauty resonates deeply because it echoes patterns we find familiar here on Earth. The branching pattern of a galaxy cluster's filament bears an uncanny resemblance to a neural network in a human brain, to the branching structure of a lightning bolt, or to the delicate web of veins in a leaf. This is not a coincidence, it is a reflection of universal principles of network formation and energy efficiency. The universe, it seems, has a preferred aesthetic, one built upon fractals and self-similarity, where patterns repeat across scales from the microscopic to the cosmic. This recognition connects us to the cosmos in a visceral, intuitive way. We feel a sense of awe not just because the structure is vast, but because its form feels strangely familiar, as if the universe and we share a common artistic sensibility. This connection transforms the cosmic web from an alien concept into something that feels almost like home, a pattern we recognize on a cellular level. Unsurprisingly, this scientific imagery has leaped from the pages of journals into the realm of fine art, inspiring a new generation of creators. Digital artists and painters use simulations as their reference, creating breathtaking works that blend accurate astrophysics with artistic interpretation. Installations at planetariums and museums wrap viewers in immersive, three-dimensional projections of the cosmic web, allowing them to feel as if they are flying through the grandest structure in existence. Even filmmakers and video game designers have adopted this aesthetic. The look of alien worlds, futuristic cities, and cosmic gateways in science fiction is increasingly informed by the real geometry of the universe, giving their creations a grounding in scientific plausibility that makes them feel more authentic and awe-inspiring. This is a powerful feedback loop. Science provides the inspiration for art, and that art, in turn, fuels public fascination and support for the science, creating a virtuous cycle of wonder and discovery. Ultimately, this intersection of science and art does more than just produce pretty pictures. It serves a vital function in our collective understanding. The aesthetics of the cosmic web act as a gateway, an accessible entry point for people who might be intimidated by complex equations or technical jargon. A person might not grasp the intricacies of lambda-cold dark matter cosmology, but they can immediately appreciate the profound beauty of a galaxy filament rendered in brilliant light. That moment of awe, that spark of wonder, is often the first step on a journey toward a deeper scientific appreciation. It makes the cosmos feel tangible, relevant, and deeply connected to the human experience of beauty. By celebrating the aesthetic majesty of the universe, we are not abandoning rigor. We are embracing a more complete form of understanding, one that engages not just our intellect, but our emotions and our spirit, reminding us that the quest for knowledge and the appreciation of beauty are, and have always been, two sides of the same coin. Yet for all the breathtaking progress we've made in tracing the cosmic web and decoding its story, we must now embrace a moment of profound humility. The map we have drawn is magnificent, but it is still a map, and vast, uncharted territories remain, filled with mysteries that defy our current understanding. The very idea that space remembers raises a host of questions that probe the absolute limits of our knowledge. How exactly is information physically encoded in the void between galaxies? Is the preservation of memory a universal law, or is it a unique feature of our particular cosmos, with its specific blend of dark matter and dark energy? These are not minor technicalities, they are gaping holes in our map of reality, and they remind us that every answer we uncover simply reveals new, deeper questions waiting to be asked. One of the most fundamental unresolved puzzles lies in the nature of the information itself. We speak of the cosmic web storing memories, but what is the actual medium? In a computer, information is stored as bits on a hard drive. In a brain, it's stored in the strength of synaptic connections. But in the cosmos, the storage system is the fabric of space-time and the gravitational field itself. The precise mechanism for how a gravitational field encodes and preserves complex information over billions of years remains deeply mysterious. We can describe the what, the pattern of galaxies, but the how is a frontier of physics. Some theorists suggest it involves concepts from quantum information theory, where the geometry of space is literally built from entangled quantum bits. Others look to the holographic principle, where the information for our three-dimensional universe is actually stored on a two-dimensional boundary at infinity. These are compelling ideas, but they remain largely in the realm of mathematical conjecture. We lack the experimental tools to test them directly, leaving us with a beautiful map of the cosmic memory without a clear manual for how its storage system actually operates. This connects directly to the enigma of dark energy, the mysterious force causing the universe's expansion to accelerate. From the perspective of cosmic memory, dark energy is the ultimate wild card. Its nature will determine the final fate of the cosmic record. If dark energy behaves as a simple cosmological constant, its strength unchanging over time, then the acceleration will continue, eventually pushing most of the universe beyond our observational horizon and erasing countless chapters from the view of any future observers. But if dark energy is something more dynamic, a field that evolves or interacts with itself, its influence on the cosmic web could be far more complex. Could it somehow alter the way information is preserved? Might it even, in some speculative models, be linked to the processing of information itself? We simply do not know. The nature of dark energy is arguably the single greatest unsolved problem in cosmology, and until we crack it, we cannot truly know how long the universe's autobiography will remain legible or what its final chapter will ultimately say. Furthermore, our entire understanding rests on the shoulders of computer simulations, but these digital universes have their own inherent limits. They are approximations bound by the finite power of our computers and the cleverness of our shortcuts. We cannot simulate every particle. We use tracer particles to represent vast clouds of dark matter and gas. We cannot directly model the formation of a single star, so we use simplified recipes called subgrid physics to estimate their effects. The concern is that these necessary simplifications might be smoothing over crucial details. Are we missing subtle, small-scale phenomena that have a cumulative effect on the large-scale structure of the cosmic web? Could there be unknown physics at the quantum level or within black holes that contributes to memory in ways our simulations cannot yet capture? The fact that our best simulations produce universes that look very much like our own is encouraging, but it doesn't prove they are correct in every detail. There may be entire layers of complexity in the universe's memory system that we have not even begun to imagine because our models are not yet sophisticated enough to reveal them. This journey into the unknown is not a sign of failure, it is the very engine of science. Every one of these mysteries is a beacon calling to the next generation of physicists, engineers, and dreamers. They are the unanswered riddles that will drive the design of even more powerful telescopes, the development of even more sophisticated simulations, and the birth of even more revolutionary theories. The story of cosmic memory is still being written not just by the universe but by us. Our curiosity is the pen, and our humility in the face of the unknown is the ink. The greatest discovery is not the answer, but the realization of how much more there is to discover. But what if our universe, with its intricate remembering web, is not the only one? What if it is just a single volume in an infinite library of realities, each with its own physics, its own history, and its own unique way of preserving memory? This is the breathtakingly speculative realm of multiverse theory, a concept that pushes the idea of cosmic memory to its absolute limits. The theories that suggest this possibility, like eternal inflation and string theory, don't just give us more universes to ponder, they force us to ask a profound question about memory itself. If a tree falls in a forest in another universe where the laws of physics are different, does it make a sound? And more importantly, could that sound, that event, leave any kind of permanent record? The most well-grounded path to a multiverse comes from an extension of the same inflationary theory that explains our own universe's beginning. The idea of eternal inflation proposes that the rapid, exponential expansion of space-time that created our cosmos isn't a one-time event. Instead, it's a perpetual process happening across a vast, meta-universal landscape. In this view, our entire observable universe is just one pocket within this endlessly inflating megaverse. Inflation stopped here, allowing matter to form and stars to ignite, but it continues unabated in the space beyond, constantly giving birth to new pocket universes. Crucially, the way inflation ends in each pocket, a process called quantum tunneling, can happen in slightly different ways. This means each new universe can emerge with a different set of physical constants and fundamental laws. In one universe, the force of gravity might be stronger, leading to a cosmic web that collapses into black holes almost instantly. In another, the weak nuclear force might be too weak for stars to ever form, resulting in a dark, inert cosmos with no structures to remember anything at all. The memory of each universe would be dictated by its unique rulebook. A universe where electromagnetism is dominant might remember its history through intricate crystalline structures on a galactic scale, while a universe governed by entirely unknown forces could encode information in ways we cannot even begin to imagine. This concept finds even more exotic expression in string theory, which suggests that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. The way these strings vibrate determines the properties of particles and forces we observe. However, string theory allows for a staggering number of possible stable configurations for these extra dimensions, perhaps 10 to the 500 or more. Each configuration corresponds to a universe with a different set of physical laws. This is known as the string theory landscape, a vast, abstract terrain of possible universes. Our universe, with its specific constants that allow for galaxies, stars, and life, is just one point in this landscape. From this perspective, the cosmic memory we've been tracing, the specific pattern of the web born from our particular quantum fluctuations, is not a universal truth. It is a local custom, a regional dialect in the grand scheme of existence. The very concept of a memory stored gravitationally in a filamentary web might be parochial, a quirk of our universe's particular physics that is utterly meaningless in the cosmos next door. This leads us to the ultimate question about memory in a multiverse: persistence. In our universe, we see memory as a thread connecting past to present, a chain of causality that ensures events have consequences that are recorded in the structure of reality. But if the multiverse is real, that chain might not just be broken, it might never have existed in the first place. In the eternal inflation model, each pocket universe is causally disconnected from the others from the moment of its birth. They are islands in an ever-widening sea of inflating space, forever beyond each other's horizons. An event in one universe cannot influence or leave a mark upon another. There is no common archive, no meta-cosmic library where the histories of all universes are stored. The memory of each universe is entirely self-contained and ultimately isolated. When that universe meets its end, whether in a heat death or a big crunch, its entire history, its entire memory, might be erased completely, with no backup and no record left anywhere else. The multiverse, in this light, could be the scene of ultimate forgetfulness, where countless stories are written and then destroyed, unread and unremembered by anything outside themselves. This dizzying expansion of perspective can't help but pull our focus back to ourselves, to our own identity and our place in this potentially infinite ensemble. The Anthropic Principle, a controversial but compelling idea, suggests that we find ourselves in a universe with laws that allow for our existence precisely because we are here to observe it. We couldn't exist in a universe without stars or atoms, so we naturally find ourselves in one that has a rich cosmic web and a long, memorable history. This doesn't explain why our universe has these laws, but it does frame our existence and our ability to ponder cosmic memory as an integral part of this universe's specific story. Our quest to trace the filaments of the web is not just a scientific endeavor. It is our universe becoming consciously aware of its own memory, a remarkable and perhaps rare phenomenon in the grand multiversal scheme. It invites us to see ourselves not as accidental inhabitants of a random cosmos, but as the means by which this particular universe, with its specific set of physical laws and its unique historical record, can reflect upon and appreciate its own narrative. In a possibly infinite multiverse of silent, unremembering, or forgotten cosmos, our ability to even ask these questions becomes a profoundly significant part of our own local cosmic memory, a unique chapter in one very special volume in the infinite library of reality. Now let's take a speculative leap into one of the most tantalizing ideas in all of science fiction and theoretical physics, the concept of time travel. It might seem like a wild departure from our discussion of cosmic memory, but the two are deeply intertwined in a fascinating way. At its core, remembering is a form of time travel. When you recall a childhood birthday, your mind is, in a very real sense, revisiting a moment in your personal past. Now, scale that idea up to a cosmic level. When our telescopes capture the light from a galaxy a billion light-years away, we are not just seeing a distant object, we are literally looking a billion years into the past. We are remembering the universe as it was when that light began its journey. In this way, every astronomer is a time traveler, and every observatory is a machine for visiting the past. This connection becomes even more intriguing when we consider the wilder edges of theoretical physics. Einstein's theory of general relativity allows for the mathematical possibility of structures that could create shortcuts through spacetime. The most famous of these are wormholes, often visualized as a tunnel connecting two distant points in the universe. But if one end of the wormhole were to be moved or kept in a different gravitational field, the two mouths could experience time at different rates. This could, in theory, turn a wormhole into a time machine. Step into one mouth in the year 2050, and you could emerge from the other mouth in the year 20,050. Or even 20,000 BC. Now imagine if the cosmic web itself, with its vast gravitational wells and complex curvature of spacetime, naturally contained or facilitated such structures. The filaments and nodes of the web might not just be a record of the past, they could potentially be a network of portals to it. Accessing a cosmic memory wouldn't just be like reading a history book. It could be like stepping through a door into that historical moment itself. Another theoretical construct that blurs the line between memory and time travel is the idea of a closed time-like curve. In certain solutions to Einstein's equations, it's mathematically possible for the path of an object through spacetime to loop back on itself, allowing it to return to its own past. If such a thing were possible, an event could become its own cause, creating a loop where information or even an object could exist without a true point of origin. This presents a profound paradox for cosmic memory. If the universe's history contains such loops, its memory would be a tangled, self-referential knot. The initial conditions we see in the cosmic microwave background might not be a true beginning, but merely one point in an endless cycle. The cosmic web would then be less a linear record and more a complex, looping pattern where past, present, and future are inextricably linked, challenging our very definition of what a memory even is. This naturally leads us to the famous grandfather paradox, a staple of science fiction that becomes a serious physics problem. If you could travel back in time and prevent your own grandfather from meeting your grandmother, you would prevent your own birth, making your time travel impossible. It's a logical inconsistency that suggests such travel cannot be possible. However, some physicists like Igor Novikov proposed a self-consistency principle which states that any actions taken by a time traveler were always part of history. You couldn't change the past because you had already been there. Your actions would only ever ensure that events unfolded exactly as they always had. Applying this to cosmic memory, it suggests that if the universe's past is accessible, it is also immutable. Any attempt to change a memory would simply be the event that solidified it, making the cosmic record a fixed and unchangeable tapestry. Your journey to witness the Big Bang would not be an intervention but a predestined part of the event itself, your presence already woven into the fabric of that first memory. While this is thrilling speculation, we must ground it in the harsh light of physical reality. The known laws of physics, particularly quantum mechanics, seem to throw up formidable barriers to backward time travel. The energy requirements to stabilize a wormhole are astronomical, requiring a form of exotic matter with negative energy density that we have no idea how to create or contain. Furthermore, the second law of thermodynamics, with its inevitable increase in entropy, creates a powerful arrow of time that seems to point only forward. The universe appears to have a strong preference for forgetting, not remembering, in its constant slide toward disorder. This suggests that while accessing the past through light and memory is a fundamental feature of our cosmos, physically revisiting it may be forever beyond our reach, locked away by the very laws that allow the universe to remember itself in the first place. Yet, the mere fact that our best theories of reality allow us to so compellingly play with these ideas is a testament to the deep and mysterious connection between the structure of space, the flow of time, and the nature of memory itself. Of course, the quest to understand cosmic memory might seem like a journey reserved for astrophysicists with access to supercomputers and space telescopes, but the truth is far more democratic and exciting. You don't need a PhD to begin tracing the filaments of the cosmic web for yourself. A world of incredible educational tools has been designed specifically to bring these vast, abstract concepts down to earth, making them tangible, visual, and deeply engaging for curious minds of all ages. This isn't about dumbing down the science. It's about translating it, using creativity and technology to build bridges of understanding that allow anyone to grasp the universe's grand narrative. One of the most powerful gateways is the modern digital planetarium show. Gone are the days of simple star projectors. Today's planetariums are immersive, all dome theaters powered by sophisticated software that can fly you through the universe at light speed. Shows like Dark Universe, produced by the American Museum of Natural History, or A Journey to the Stars, use real scientific data from missions like Planck and Hubble to visualize the cosmic web in breathtaking detail. Sitting back in your seat, you don't just hear about dark matter, you watch it coalesce into a shimmering golden scaffold across the dome above you. You don't just learn about galaxy collisions, you witness them unfold in a slow-motion ballet of gravity and light, feeling the scale and dynamism of the universe in a way a textbook could never convey. These experiences are more than just movies. They are visceral voyages that transform statistics and equations into a profound sensory understanding, leaving audiences with a lasting sense of awe and a clearer picture of how the universe structures itself. For learning from home, the internet is an unparalleled treasure trove. Interactive simulations are perhaps the most direct way to play with the forces that shape cosmic memory. The website, Universe in a Box, offers simple but powerful browser-based tools where you can adjust parameters like the amount of dark matter or dark energy and instantly see how those changes affect the formation of the cosmic web in a simulated universe. For a more hands-on experience, the Cosmic Web project from the University of Leiden allows you to explore a 3D model of the local universe, zooming in and out of filaments and voids, and clicking on individual galaxies to learn about their properties. These tools demystify the science by putting you in the driver's seat, allowing you to experiment with the very building blocks of reality and see the cause and effect relationships that govern cosmic evolution firsthand. For those who prefer a more structured learning path, massive open online courses or MOOC offer incredible depth. Platforms like Coursera and edX host courses from top universities like Caltech and the University of Chicago with titles like The Science of the Solar System or Galaxies and Cosmology. These courses often include modules specifically on large-scale structure, featuring video lectures from leading researchers, interactive quizzes, and detailed visualizations that break down complex ideas step by step. They allow you to learn at your own pace, diving as deep as you wish into the mathematics and physics behind the cosmic web, all while being guided by some of the world's foremost experts. It's like auditing a world-class university course from your living room, with all the resources you need to truly master the concepts. Beyond formal courses, the YouTube channels of major scientific institutions have become a phenomenal free resource. NASA's Goddard Space Flight Center channel regularly releases new visualizations that turn satellite data into stunning fly-throughs of nebulae and galaxy clusters. The European Space Agency's channel offers in-depth documentaries on missions like Euclid, which is currently mapping the dark universe. And channels like PBS Spacetime or Kurzgesagt take complex topics like the Holographic Principle or Entropy and explain them with clear narration, engaging animations, and thoughtful analogies that make the seemingly impenetrable not only accessible but thrilling. These videos serve as both brilliant introductions and deep dives, perfect for sparking a new interest or satisfying a burning question. The impact of these tools extends far beyond simple understanding. They are actively inspiring the next generation of scientists. When a middle school student uses a simple simulation to watch a galaxy form, or a high schooler completes an online course module on dark matter, they aren't just memorizing facts. They are developing an intuition for how the universe works. They are seeing themselves not as passive observers, but as potential participants in this great exploration. These experiences can plant a seed of curiosity that grows into a passion, guiding career choices and shaping the minds that will one day build the next generation of telescopes and solve the mysteries we can today only dream of cracking. By making cosmic memory accessible, we aren't just sharing knowledge, we are nurturing the future guardians of that knowledge, ensuring that the incredible human project of understanding our place in the cosmos continues to grow and flourish for generations to come. Imagine for a moment the sheer volume of data pouring in from our most powerful observatories. The upcoming Vera C. Rubin Observatory, for instance, will image the entire southern sky every few nights for a decade, generating over 20 petabytes of raw data. That's a stack of DVDs reaching to the moon and back. Hidden within that unimaginable flood of ones and zeros are the subtle patterns of the cosmic web, the faint filaments, the precise distances between galaxies, the weak gravitational lensing distortions that trace the dark matter. For a human astronomer, finding these patterns would be like trying to find a single specific grain of sand on all the beaches of Earth by hand. It's an impossible task, which is precisely why we've had to enlist a new kind of partner in our cosmic archaeology: artificial intelligence. This isn't about replacing human curiosity. It's about augmenting it with a formidable new set of senses. Machine learning algorithms, particularly a type called neural networks, are being trained to see what we cannot. The process begins with the simulations we discussed earlier. Scientists feed these AI systems thousands of highly realistic, virtual universes created from our best models of cosmology. The AI learns the rules of the game. It studies what a dark matter filament looks like in the data, how a cluster of galaxies should statistically behave, and what the telltale signs of gravitational lensing are. It learns to distinguish the real cosmic signal from the inevitable noise of telescope sensors, atmospheric interference, and the sheer randomness of the universe. Once trained, this digital expert is unleashed on the real data. It can scan millions of galaxy images in the time it takes a human to examine one, classifying shapes, measuring distances, and identifying the faint, gossamer thin bridges of gas that connect the nodes of the web. It's like giving a master archivist a team of millions of superhuman assistants, each capable of scanning entire libraries in seconds and flagging the most crucial passages for further study. A spectacular example of this partnership in action is the European Space Agency's Euclid mission. Euclid is designed to create the largest and most accurate 3D map of the universe ever made, charting billions of galaxies across 10 billion light-years. The data it will send back is so vast and complex that traditional analysis methods would take centuries. So, from the very beginning, AI was baked into the mission's DNA. Machine learning algorithms are being used to do everything from calibrating the spacecraft's incredibly sensitive optics to identifying and measuring the subtle distortions in galaxy shapes caused by dark matter's gravitational lensing effect. This weak lensing signal is incredibly faint. The distortion on a galaxy's shape is often less than 1%. It's a change imperceptible to the human eye, but an AI trained on countless examples can pick it out with astonishing precision, allowing us to trace the invisible dark matter scaffold with unprecedented clarity. Euclid's AI isn't just a tool, it's a core part of the instrument, translating the raw light from the cosmos into a readable map of its hidden memory. But the role of AI goes far beyond just finding what we tell it to look for. Its most exciting potential lies in discovery, in finding patterns that we humans didn't even think to search for. This is the realm of unsupervised learning, where algorithms are simply turned loose on the data without any preconceived notions or training on what to expect. They are tasked with finding the anomalies, the oddities, the statistical outliers. In doing so, they might stumble upon entirely new types of celestial objects or uncover unexpected relationships within the cosmic web that challenge our existing models. An AI might analyze the distribution of galaxies and discover that they cluster in a way that doesn't quite fit the standard model of cosmology, potentially pointing toward new physics or a deeper understanding of dark energy. It's the equivalent of a master detective who not only solves the case you gave them, but also discovers a whole new conspiracy you never knew existed. This synergy is the true revolution. The human mind asks the big, bold questions about the nature of memory and existence, and the artificial mind provides the computational power to find the answers hidden in the light, often revealing new questions we were never smart enough to ask on our own. This journey into the structure of memory inevitably leads us to one of the most profound and provocative questions we can ask. Does the universe, in remembering itself, also in some way experience that memory? Could the vast, intricate cosmic web be more than just a passive archive? Could it be a form of brain, and the universe itself a form of mind? This is not a new question, but it is one that gains startling new resonance when we consider the cosmos as a dynamic, information-processing network. Some of the most daring thinkers in philosophy and theoretical physics are now exploring the idea that consciousness might not be a rare and recent accident in a lifeless universe, but a fundamental property of reality itself, with the cosmic web as its most magnificent expression. This concept finds its boldest voice in a school of thought known as Panpsychism. From the Greek words pan meaning all and psyche meaning soul or mind, Panpsychism proposes that consciousness is not something that magically emerges from complex arrangements of non-conscious matter, like a rabbit pulled from an empty hat. Instead, it suggests that consciousness is a fundamental and ubiquitous feature of the universe, as basic as mass or charge. In this view, even the most elementary particles possess an infinitesimal spark of subjective experience, a mere whisper of what it is like to be that particle. Of course, an electron isn't conscious in the way a human is. It doesn't have thoughts or feelings, but it might possess the most basic precursor to consciousness, a tiny bit of proto-experience. Panpsychism argues that when these fundamental particles combine into increasingly complex systems, atoms, molecules, cells, and eventually brains, these tiny sparks of experience combine and amplify, giving rise to the rich, complex consciousness we experience. Apply this to the cosmic scale, and the implications are staggering. The cosmic web, as the most complex structure in existence, woven from trillions of galaxies, each containing billions of stars and planets, could therefore be the seat of a consciousness so vast and alien that we can scarcely imagine it. Its memories wouldn't be stored like data on a hard drive. They would be lived, experienced, and integrated into a cosmic form of awareness. This idea moves from philosophical speculation toward a potential scientific framework, with a theory developed by neuroscientist Giulio Tononi called Integrated Information Theory, or IIT. IIT attempts to mathematically measure consciousness. It doesn't ask what a system is made of, but how its components are organized. The central quantity in IIT is called phi, a number that represents a system's ability to integrate information. A system with high phi isn't just storing information, it's processing it in a unified way where the whole is greater than the sum of its parts. The human brain, with its trillions of densely interconnected neurons, has a very high phi. A digital camera sensor, which captures lots of information but doesn't integrate it in a unified way, has a very low phi. Now consider the cosmic web. Its nodes are galaxy clusters, and its filaments are flowing with matter and energy. Gravity provides the connection, creating a network of immense complexity and causal influence. While the timescales are unimaginably slow, the system is processing information. Gravitational influences move at the speed of light, matter flows, and feedback loops operate over billions of years. Could this system have a phi greater than 0? If IIT is correct, then the answer might be yes. The universe, through the cosmic web, might not just contain information. It might be integrated enough to possess a faint, cosmic-grade form of consciousness. Its memory would be an integral part of that conscious experience, a timeless knowing of its own structure and history. This forces us to re-examine the very relationship between memory and mind. We typically assume that memory is a product of consciousness, that a mind is required to have memories. But what if the reverse is also true? What if the existence of a stable, structural memory is a prerequisite for any form of consciousness? A system that cannot retain information from one moment to the next, that has no continuity, could never have a unified experience. In this light, the cosmic web, by preserving the imprints of the Big Bang for over 13 billion years, has created the ultimate substrate for continuity. Its staggering stability provides the permanence needed for a consciousness that operates on cosmological timescales. The universe remembers, therefore it has the potential to be aware. This perspective turns the question inside out. We don't need to ask if a conscious universe is remembering itself. Instead, we can see that its profound, structural memory is what makes any form of universal consciousness possible in the first place. The memory is not a byproduct of the mind. The memory is the foundation upon which a mind could be built. Naturally, these ideas are met with deep skepticism from many corners of the scientific community. The most common criticism is that they are not falsifiable. How could we ever test whether the universe is conscious? It is the ultimate solipsistic claim, impossible to verify from within the system we are trying to measure. Others argue that applying theories like IT to cosmic structures is a category error, a misleading analogy that assigns human-like properties to systems that are utterly different in kind and mechanism. The feedback loops in a galaxy are not analogous to the electrochemical signals in a brain, no matter how pretty the pictures look side by side. Yet, even as a metaphor, the idea is powerfully useful. It provides a new lens through which to view the cosmos, inspiring new questions about information flow, causality, and complexity. It challenges our anthropocentric assumption that consciousness is a singular miracle unique to earthly biology. And it deeply resonates with the intuitive, almost spiritual sense of connection many feel when confronted with the majesty of the night sky, a feeling that we are not just looking at the universe, but that we are a part of it looking back at itself, participating in a grand, conscious act of remembrance that has been underway since the very first moment of time. But this grand idea of a remembering universe doesn't just live in the realm of distant galaxies and abstract physics. We are surrounded by living, breathing examples of memory systems right here on our own planet. Earth itself is a master archivist, preserving its history in ways that offer a powerful and tangible analogy for the cosmic processes we've been exploring. By looking down at our own world, we can find a familiar mirror to help us understand the strange and vast memory of the cosmos. Consider the humble tree standing tall in a forest. When you cut into its trunk, you don't just see wood, you read a history book. Each ring tells a story of a single year in that tree's life. A wide ring speaks of abundant rain and long, sunny days. A narrow, tight ring whispers of drought and hardship. You might even find the scar of a long-ago forest fire, a permanent record of a traumatic event that the tree endured and grew around. This isn't just a metaphor. It's a literal, physical encoding of environmental information over time. Now, scale that idea up. An entire forest is a vast library of these arboreal records. By comparing trees across a region, scientists can cross-reference these memories, building a precise timeline of the local climate stretching back centuries. This is dendrochronology, a terrestrial form of cosmic archaeology, where the medium isn't dark matter but cellulose, and the information isn't gravitational collapse but rainfall and temperature. This biological memory extends far beyond trees to the very code of life itself. An organism's DNA is perhaps the most efficient and ancient information storage system we know. It's a molecular library that holds the entire evolutionary history of a species. Woven into your own genes are memories of ancient adaptations, the ability to digest certain foods, resist specific diseases, or even the reflex to startle at a sudden loud noise. These are echoes of survival strategies that worked for your ancestors millions of years ago, preserved and passed down through generations. This genetic memory is not unlike the way the cosmic web preserves the initial conditions of the universe. The first life forms on Earth established a basic genetic blueprint, and evolution, like gravity, has acted upon it, amplifying successful traits and allowing complexity to grow. The diversity of life we see today, from a bacterium to a blue whale, is the biological equivalent of the cosmic web's intricate structure, all emerging from a preserved and continuously interpreted primordial record. And then there's the planet's most dramatic memory keeper, the fossil record. When a creature dies and is buried under layers of sediment under the right conditions, its form can be mineralized, turned to stone. This process transforms a fleeting moment of death into a permanent snapshot, a fossil that can survive for hundreds of millions of years. A single fossil is a memory of an individual organism. But a geological stratum, a layer of rock filled with fossils, is a memory of an entire ecosystem, a chapter in Earth's deep history. Paleontologists are the archaeologists of this terrestrial memory, carefully brushing away the dust of ages to read the stories locked in the stone. They can trace the rise and fall of dinosaurs, the evolution of mammals, and the catastrophic events like asteroid impacts that abruptly ended one chapter and began another. This is directly analogous to how cosmologists use different redshift layers to read the history of galaxy formation. In both cases, depth equates to time, and the fossils, whether ancient bones or ancient galaxies, are the preserved data points. The connections run even deeper when we consider ecological patterns. A thriving coral reef, with its specific and delicate balance of species, is a system that holds the memory of a stable environment. If the water temperature rises or becomes more acidic, the coral bleaches and dies, and that memory of stability is lost. The system tips into a new state, a different kind of memory dominated by algae and fewer species. This is a form of ecological memory loss, similar to how a galaxy merger can scramble the history of the galaxies involved. The resilience of an ecosystem, its ability to bounce back from a disturbance, is directly tied to the diversity of information stored within it, just as the stability of the cosmic web is tied to the gravitational bonds within its structure. By studying how memories are preserved, lost, and transformed in the ecosystems we can observe and interact with, we gain invaluable insights into the same processes operating on a scale so vast we can only infer them from afar. The Earth becomes our local laboratory for understanding universal principles of information, memory, and the unfolding of time itself. Long before we had satellites and supercomputers, humanity was already deeply engaged in a quest to understand the cosmos and our place within its memory. For thousands of years, we have looked up at the night sky and seen more than just points of light. We have seen a story, a clock, a map, and a mirror. This ancient, universal impulse to find meaning in the stars is perhaps the earliest and most profound expression of our intuitive grasp of cosmic memory. Every ancient culture, from the Babylonians to the Maya, from the Egyptians to the Chinese, developed sophisticated systems of astronomy, weaving the predictable motions of the planets and the fixed patterns of the constellations into the very fabric of their mythology, religion, and daily life. They observed that the cosmos operated with a regularity that could be trusted, a cyclical memory that repeated with the seasons, and they built their civilizations upon this understanding. This celestial observation was not mere curiosity. It was a matter of survival and societal order. The annual flooding of the Nile was so crucial to Egyptian agriculture that its arrival became the cornerstone of their calendar. Priests and astronomers carefully tracked the heliacal rising of Sirius, the brightest star in the sky, which appeared just before the floodwaters began to rise. This celestial event was a memory trigger, a dependable signal from the cosmos that dictated the rhythm of their entire year, governing when to plant, when to harvest, and when to make offerings to the gods. In this way, the memory of the cosmic cycle was literally baked into the bread that fed their civilization. Similarly, the Maya of Mesoamerica developed incredibly precise calendars by meticulously observing the movements of Venus, the Sun, and the Moon. Their long count calendar was a vast, interlocking system designed to track immense cycles of time, believing that history itself was cyclical and that the cosmos remembered past eras. Their elaborate temples, like the pyramid at Chichen Itza, were not just places of worship but functioning astronomical observatories. During the equinoxes, the interplay of light and shadow creates the illusion of a serpent slithering down the steps, a breathtaking fusion of architecture, astronomy, and mythology that encoded their cosmic understanding into stone, a permanent physical memory of their celestial knowledge. This deep-seated desire to see our own stories reflected in the heavens gave birth to the practice of astrology, which is fundamentally a belief in a sympathetic cosmic memory. The central premise of astrology is that the specific arrangement of the planets at the moment of a person's birth imprints a kind of memory or influence onto their character and destiny. The zodiac itself is a perfect example of this. It's a belt of the sky divided into 12 sections, each named for a constellation that ancient cultures saw as a familiar pattern: a crab, a lion, a pair of scales. They projected their own myths and archetypes onto these star patterns, creating a narrative map of the sky where the drama of the gods was forever playing out. While modern science has separated itself from astrological prediction, we must recognize that this impulse came from the same place as our modern cosmology, a profound need to feel connected to a universe that has order and meaning, to believe that the cosmos above is in dialogue with the world below, and that our lives are part of a larger, remembered story. The great pivot toward the science we know today began when thinkers started to seek the mechanisms behind this cosmic memory, rather than its mystical meaning. Isaac Newton's law of universal gravitation was a monumental leap in this regard. He proposed that the force that made an apple fall to the ground was the very same force that held the moon in orbit around the Earth and the planets in their paths around the sun. This was the first powerful mathematical formulation of a universal law, a set of rules that the cosmos remembered and obeyed consistently everywhere. Newton's cosmos was a majestic, predictable clockwork, its memory perfectly encoded in immutable mathematical principles. This shift allowed us to stop just reading the stories in the stars and start deciphering the underlying physics that wrote them. It transformed the sky from a tapestry of gods and monsters into a complex system operating under knowable laws, setting the stage for every cosmological discovery that was to follow. Our current scientific exploration, with its telescopes peering back to the Big Bang and its simulations of the dark matter web, is the direct descendant of these ancient traditions. We are still telling stories about the cosmos, but now the narratives are written in the language of mathematics, physics, and data. The quest to trace memory in the cosmic web is the modern equivalent of the Maya tracking the cycles of Venus or the Egyptians awaiting the rise of Sirius. We are still seeking that connection, that assurance that the universe is ordered and that we can understand our place within its grand timeline. The tools have changed from stone circles to space telescopes, but the fundamental human yearning to find ourselves in the stars and to understand the memory of time itself remains beautifully, powerfully the same. This long historical arc contextualizes our modern journey not as a break from the past, but as the latest chapter in an enduring human saga of wonder. And so we find ourselves at the end of this incredible journey, having traced the memory of the cosmos from the faintest quantum whisper to the grand, glittering architecture of the cosmic web. We've seen how the universe is not a blank slate, but a vast dynamic chronicle, a story written in the language of gravity, dark matter, and time, with each galaxy a sentence and every filament a paragraph in an epic that began over 13 billion years ago. This isn't just a metaphor, it is a fundamental shift in how we perceive reality itself. The silence of space is an illusion. If we learn to listen with the right tools, the cosmos is anything but quiet. It is a symphony of structure, a constant, low hum of existence remembering itself, and we have only just begun to hear the melody. This exploration does more than just satisfy our scientific curiosity. It redefines our place within the grand narrative. We are not passive observers separate from the universe, looking in from the outside. We are active participants woven into the very fabric we study. The atoms that form our bodies, our planet, and everything we hold dear were forged in the hearts of stars that lived and died long before our sun was born. Their story is literally a part of us. When we look up at the night sky, we are not just seeing distant points of light. We are gazing into a mirror, a reflection of our own deepest origins. Our drive to understand, to map the cosmic web and decode its memories, is the universe becoming consciously aware of its own history. We are the means by which the cosmos knows itself, and in that realization, we find a connection more profound than any we could have imagined. Let this knowledge change the way you see the world. The next time you find yourself under a clear night sky, away from the city lights, take a moment to truly look up. See not just the stars, but the immense, invisible connections between them. Contemplate the fact that the light falling on your eyes has traveled across space and time, carrying with it information from events that occurred millions or even billions of years ago. In that moment, you are not just a person on a planet. You are a node in a cosmic network, receiving a message from the deep past, participating in the universe's great act of remembrance. This perspective invites a sense of awe, humility, and belonging that can ground and inspire us in our daily lives. The story of cosmic memory is far from finished. In many ways, our exploration is just beginning. With every new telescope we build, every new simulation we run, and every new theory we propose, we add another line to this unfolding story. The mysteries we've touched upon, the true nature of dark matter and dark energy, the possibility of a multiverse, the quantum foundation of space-time, are the frontiers waiting for the next generation of scientists, thinkers, and dreamers to explore. This endless curiosity is our greatest gift, the engine that drives us ever forward in our quest to understand our spectacular and remembering universe. Your journey doesn't have to end here. The cosmos is waiting for you to engage with it. You can join a citizen science project and help classify real galaxies. You can dive into the breathtaking visualizations created by NASA and the ESA, or you can simply step outside and look up with a renewed sense of wonder. The universe's story is the ultimate story, and it belongs to all of us. We are all cosmic archaeologists, and the greatest discoveries often begin with a single, simple question. So stay curious, keep looking up, and never stop wondering about the endless stories held in the stars.